the
stream.
Working.
Yeah, exactly. You know, and
always. You want me to like you say like code blue and I type something and you're like yeah.
You can just yell at me. Just do a lot of yelling and telling me to hurry up, and that works. That works very well. Yeah, you know, all of a sudden impossible becomes very probable. Okay, so I'm not seeing live yet, so it may take a second for it to start. Oh, and very good. So we've got a YouTube channel up. Fantastic. We've got. I'm not going to check the other one. We know if that's working, the other ones will be working as well. And then I'm going to go to the multi-stream so I can actually sort of see some questions. Twitch requires additional permissions. Oh, really? Wow.
I also get we are live.
Good. Okay, good. Discord. Fantastic. It's always nice to know. It's nice to know you're live. So, interwebs, welcome. We are back with another I'm with Genius. I am so alarmingly excited. Because we've got Lisa Wörner back, and Lisa is my quantum queen, which I know she hates and cringes every time I say, but it was so much fun to talk to you the other day. And I actually sat down and listened to our podcast. Well, it's not a podcast, it's a chat. I hate calling it a podcast. It sounds sort of Hollywood somehow.
Well, it is. I would call it that.
But it was so much fun. It was like really... and what I loved, I've got to go pick out some bits there because there are some pieces there that really helped me understand some of this quantum stuff, the bosons and the fermions on the bus, and just how, you know, the splitting of these Einstein condensates and everything. It's just so nice to be able to chat about it, and I so appreciate you coming back, you know, kicking and screaming into the light. How are you?
I'm so happy to be here. Thank you so much. I'm great. I'm so happy. I'm so excited to be back here. And I can't wait to hear your questions, and I can't wait to see what the community has of questions. And yes, I'm really overjoyed to be back here. It was amazing. It was exciting. So looking very much forward to it.
It's just, I think what I love about these chats is that you're talking to people who just love this stuff in the way that I used to love making films and TV when I was a kid. There's just this wonderful, and I've never lost that myself. I've always the lifelong learning stuff. You give it a name, but the reality is it's just curiosity. I love trying to understand these crazy, you know, these mad things that you're doing. I went and visited a company the other day, and the whole time I was going, God, I wish Lisa was with me. It was a company called Xanadu AI, I guess. I'm not sure why it's AI, because they're a quantum computing company based out of Toronto. And so I saw all of these light-splitting mirror systems that they'd originally created, and now they're making these chips that respond. I would just love for you, I know you touched on this before, but I would love for you to talk about some of the science behind that. They're using photonics for this, which you were saying was a wonderful system because you could just basically, it didn't work, get another one. It's just that, you know. So perhaps if you wouldn't mind, maybe you could just so everyone's got it, maybe just remind us who you are, and then we can dive into some quantum talk.
Absolutely. So, hi there. My name is Lisa. I am, as you call me, your quantum queen. I will try to get used to it.
I'll get you a crown. Maybe we get like some kind of little icon that could follow your head around while you're talking. It's perfect. Yeah.
Burger King, when I was young, had these crowns, so maybe out of paper. I am with the German Aerospace Center. We are working on different types of quantum technologies. The German Aerospace Center also has a quantum computing initiative where we are looking especially into fostering quantum computing and trying to get startups and people involved and try to advance the technology is what I'm trying to say. I told you before, my English today is not on par. I don't know what happened.
That's right. Neither's mine, and I speak it. I mean, like, that's my language, so, yeah.
I mean, I can switch to German. I'm not even sure if that would make things better. But anyway.
I got 14% on a German exam, so I think that probably better we stick with English.
Yeah. All right. only this time.
Yeah, thank you. Danke.
Yeah. There you go. You're most welcome.
It all comes flooding back. That was it.
Right? It all comes in half an hour we'll be speaking German.
Yeah, basically, yes. Yeah.
So, yes, I'm with the German Aerospace Center, trying to look into quantum technologies. Our focus here at the institute that I work at is to use cold and ultra-cold atoms Bose-Einstein condensates, Fermi gases we talked about the last time, to build inertial sensors, to build gravimeters, gradiometers, to build clocks. We also touched on clocks, to apply that to Earth observation, make sure that these systems operate properly in orbit. So all these kind of things are where my focus is at. DLR, of course, is bigger than that. I touched on the Quantum Computing Initiative. We also have an institute that looks into magnetometers, quantum key distribution, quantum communication, as you would call that. And then we have an institute which is called Communication Navigation, and they do all kinds of things, and we try to work together to make it happen. The biggest project at our institute right now is called BCAL, the Bose-Einstein Condensate and Cold Atom Laboratory. You can hear all the words, big words.
Good. That's a good one. It's a good one. Beacon, it works. Yeah.
Where we try to bring a cold atom ensemble to space, to the International Space Station, and perform all kinds of things with it. And the amazing thing about space is, it's super exciting. I mean, you've been, right? So it's super exciting.
For me, space was very uncomfortable because it was all hanging from wires and things. I think space might actually be more pleasant.
Probably.
Just like a giant wedgie for me.
They won't take me along, which I'm still kind of...
Yeah, I remember that. That's floating away during our chat as you started dreaming about astronauts. Yeah, it's true.
Yeah, there we go. Also that. But that's also a different story. Anyway, this is what we're trying to do. And the other fun thing about space is that when you develop something for space, you do a lot of things that you need for Earth operations. So you have them autonomous, because you don't have a PhD student on board who can splice the fibers or readjust the optics or do whatever to the system. So the system has to be fully autonomous. It has to be robust, so it has to be kicked around and launched and whatever and carried around or transported around. And it has to be resilient, meaning if it goes down, it has to come back up very quickly. And it has to be small. And it has to use a certain amount of power that is given to it, and you can only exert a certain amount of heat and stuff like that. So
incredibly limited resources, isn't it?
Yes, very limited resources. And if you take those, these are also the things that you would want from a phone, for instance, for something that I give you. I don't want to give that to somebody or limit my potential buyers to people who have a PhD in quantum mechanics. I want to be able to give that to any person, basically, in the end, and tell them, put that in your car and it will navigate you. And so this is where the technology transfer from space back to the ground comes in for us, and also the future operation of these systems in space. But now I'm in the middle of things, because you've also talked, I've seen that you've talked about gravimetry and gradiometry and all these kind of things where we can also use the system that we now bring to space to have more exact data and do these kind of things. And my wildest dream right now is to bring that to Mars for some weird reason.
Why Mars? Why the fascination with? I mean, I get it. I get obviously the fascination with Mars, but yeah, for you, what's the appeal there?
So
it feels like a miserable place to me. I mean.
Yes, it is. There is. So the first thing is, for me, I was looking into the sensors. I wanted to advance the sensors, to have the sensors be further developed and have those, the quantum sensor in and of itself, the atom interferometer, have those ready for.
You want to build stuff. You want
I want to build.
I want hands-on. Enough of this quantum talk. I want to make something. Yeah, got it.
I want to make something. Yeah. And I want to make it in a sense that everybody understands why I'm making it. I don't need you to understand. I mean, we are going to talk it. I'd love for everybody to understand that. And there's the Douglas Adams situation where he comes back to Earth and he's like, yeah, I lived in this advanced civilization, but I've got no clue how things work. And I don't want to come into that situation. So I'm happy to explain it. I love to explain it. But in the end, I want to come into a situation where I say, yes, it's an inertial measurement unit. And we will all be quiet because we all know what it has to do. And nobody really needs to understand how it works, like my phone.
Right. We don't talk about cars as being internal combustion engines. We call them cars. You know, there's a
cars.
or electric vehicles.
Because, I don't need to know how the car works. I mean, I do sort of, but I don't need to really know how it works as long as I understand why I need it. So that's
it's just that interface that allows you to do what it needs to do, type thing. Right. Okay.
Yeah. Exactly. And so, developing these sensors for me is it's important to develop them into a way and develop and further them to make sure that we have the intended usage out of them, or that we get the excitement out of them. And one way, we are the German Aerospace Center, so space is in our name. We want to do space. there has been a lot of talk of using these systems in Earth observation. But Earth observation, especially climate change, is something that is so important that people get very hesitant of trying to use new technologies. And I understand that.
Really? I don't. Why? What's the deal?
The idea here is to have reliable data and to send another reliable satellite up in space and make sure that you get the reliable data and that you get the data that you understand and that you can compare to the data. Yeah.
Right.
I mean, there are missions that want to go the next step. And there are pathfinders to go the next step. And all these things are super important. But there's always a bit, or at least I feel a little bit of that reluctance. Probably the colleagues from ESA are going to call me in half an hour and are like, Lisa, please stop talking about that. But this is... right. This is
I just love that ESA calls you to yell at you. That's fantastic. You know, that's
yeah. We will see. Or maybe my boss calls me and tells me to stop talking about ESA. But anyway, so I felt a certain conservatism, and I was like, where else would I want to know something about the gravitational field? What other planetary body? What other idea would I have? And the first one was the moon. But
that was my first one too. Yeah.
The moon doesn't have an atmosphere. So it doesn't need that kind of system. I can go into explaining how the system works, but it doesn't need that kind of system. And because it doesn't need that kind of system, there has been the so-called GRACE mission. So the mission for Earth is GRACE. It's called GRACE. Gravity and Climate Recovery Explorer, probably. I don't know. I have
not bad. Yeah.
Something in that direction.
Sounds good. I'm buying it.
And so GRAIL is the same type of mission for the moon. And it doesn't need any inertial measurement units because there's no atmosphere to measure. So you just measure the gravitational field, life's good. So that has been done. So the moon was out of the picture.
Okay.
And then I just went with the flow. So the next two candidates seem to be Venus and Mars. And
I got to say, Venus seems a lot more appealing to me. I mean, not to live or anything, but just from a mystery standpoint.
To investigate.
But anyways,
but Venus has a very dense atmosphere.
Yeah.
So actually Mars seems to be, if you want as low an atmosphere as possible. I also thought about Jupiter and Jupiter's moons and stuff like that. So this would be another idea to go even further out.
But Mars makes the most sense between the dreams, the quantum queen dreams, and the reality of actually getting something made. Got it. Okay.
Yeah, and then in addition to that, and this is something, again, you can tell me that this is stupid, or you can shun me for this, but in the end, I also have to follow the flow. Right. And the flow currently of the big space agencies, where the money is to go towards Mars. So if I can aid the idea of bringing robots to Mars, or investigating the planet, or understand what is happening, planetary dynamics, I talk to now a lot of planetary scientists who say it's the lithosphere and the movement of the lithosphere and melting of water and whatnot. And I originally very naively said, well, what about underground water? And I would like to know whether there's water and where it is, and aquifers and stuff like that. And all of that you should potentially get from the gravitational field. And we're discussing
because you're detecting the difference in the responses you're getting from these quantum sensors,
from the satellites. It's these following satellites. I think you've had that on one of your.
But this makes sense though, because I mean the reality is you need that economic sort of horse to draw the research cart, don't you? I mean, there's not you can't just the cart doesn't work very well without the economics, right? So
it doesn't. I mean, if the science case, I can make that science case for any planet in the solar system, but it's sort of if I
Mars
get
is hot.
Exactly. If I get the additional push, if I can use the additional political push, and maybe by just talking to it so openly now to a wide audience, I'm just going to destroy that. But the thing is, if I use that push, if I use that interest to foster to further my sensors, I'm going to do it. I'm going to be that opportunistic. And I think Mars is interesting.
Oh, absolutely. Yeah. I mean,
for me, it's more about sending the satellite, sending the sensors out, and I was overjoyed when I talked. And here I have a similar feeling as you do. It's so fun to talk to people who are happy about their field of research, and I get so excited. And it's a Dutch colleague in this case, whom I love dearly, and him and I, it's whenever I meet him, I'm like, yes, let's do that, yes. And so. He's super excited about Mars, about the planetary dynamics and waters and whatnot that you can have, right? And atmospheric disturbances and all these kind of things that you can measure. And I'm super excited about the sensors. And so here we are together, super excited about a potential mission to go to Mars.
And what is and where is that potential right now? Where does that stand? Is that something that seems like doable next to? I mean, the American side of me, I'm American, Canadian, and British, so I feel like I'm an outcast in all of them. But in America, I know they're talking about pushing for a Mars landing of some sort, amongst many other things that are going on.
You see, that's exactly the push that I mean.
Yeah.
People are talking about going to Mars, and this would be some sort of precursor, right? We could say that we could tell you about landing sites. We could tell you about maybe the most interesting part to land on, because we see something in the gravitational field that maybe there's a cave, or maybe it's very solid, depending on what you're looking for.
You're selling the shovels and the pickaxes. It's very smart. Very smart. You know, because they're going to need that if they want to get there. Look at you! You're like not just the quantum queen. You're like the business savvy queen here too. You got You can have a YouTube channel.
You have exposed my manipulation tactics. But
You're
so
good.
Yes, that is exactly what we're looking at, and why this might be, or where water is. Like if I understand that in this region there's a lot of water, or something is different in this region, then this might be a very interesting point to land on and to investigate. And so I want to do that. It's probably going to happen in parallel before you land, or as a preparation for. And it doesn't matter how realistic I think humans on Mars are, because that's not. If somebody says they want to send humans to Mars, then I'm just going to use it as an argument.
Have a sensor. Yeah, got it.
Yeah, have a sensor. Here you go. I tell you where there's water. If you want to send a human, this might be a good place to send them.
Fine.
So there you are.
Yeah.
This is sort of the idea that I have behind that.
Well, and what great information to have too. I mean, the reality is we're pulling these, that with examining the asteroid sample and finding the building blocks of life there. They've got the Mars stuff's going to be coming back. I mean, we're so close to putting it together. I'm really kind of excited about that too. So water is, of course, being a massively important part of all this entire process.
Yes. Yeah. There's also something which is called comparative planetology, where you look at a planet. For that, Venus might be a little bit more interesting, but you look at a planet and you look at its current state and you say, well, from what we understand, this is how the development looks, and this might be the future of Earth, or this might have been the past of Earth, and this is how we understand how the continents formed and something like that, or how volcanoes form, or, whatever, because it's maybe easier to observe that in a system that is Mars, where you have fewer vegetation and fewer life in that sense, where it's a little bit cleaner.
You can see how it was developed without our, as you say, of course, I didn't even think of it. Like the vegetation and animals and stuff are going to have an impact so you don't see the pure sort of like space version of the planet. Yeah, that's interesting. I hadn't thought of that before. Yeah, we're totally on the way on that stuff.
Yeah, so and these are all things where I think that this mission gets me super excited.
I'm excited now too, and I wasn't even a big Mars fan to start, but I'm all for that.
There you go.
Yeah. If it takes, I suddenly had an insight into why you are doing what you're doing, because you are sitting in a position where you've got this love of the science and the practical business sense to put these stuff together, and that is a skill that I don't see a lot in this. Often you talk to scientists and it's pure science, and it's, if only it was in a perfect, this combination is deadly. Lisa, you are. This is exciting.
We are live on air. You can't say these things.
I can't say nice things. Okay. All right. Sorry. No, never again.
I'm not a good I'm not, no, I don't do that. Thank you.
But it's just interesting to see, because I think it's a side of science that we tend to forget. Like there is, it's not just science and the difficulty of figuring stuff out that's the problem. It's the difficulty of how to get people to help us figure out what's going on. And I think that's something that I think is important for people, and is a skill that other people might have that may not be drawn directly to the science, or, so.
And as much as I love, so when I started studying back in the day, we had a discussion about what I would like to do with my life. And I answered, I just want to be, back then I thought I want to answer the biggest questions of the universe.
You're doing it.
Now, Yeah, now I'm saying I would love to be part of the problem. Like, I would like to be the one like, that looks strange.
Ha.
What's that?
Ha.
Right? This is the physicist. The physicist part of the problem.
You want to be
part of
McKay.
the solution. Yeah, I want to be like, this looks weird.
Yeah.
What is that? And the other reality to all of that is that thinking about stuff and discovering the world and discovering the universe is very good in its own right. But we can never forget that we do this with taxpayers' money. And so bringing something back to society, making sure that we have an industrial impact with that we can foster our technologies, make a better world out of that.
How do we improve people's lives by the science that we're doing? Yeah, it's very smart. Yeah.
I don't know if I talked about that last time, but there is something that I coined green quantum.
Oh yeah,
so using quantum technologies for climate change, and this for me is something that is it sort of falls into that, right? Like, how can I use my understanding of a sensor, of a type of technology, to make the world a better place? And this is, I mean, this is like I'm missing the English word now. It's a bit too big. It's giving it a bit too much emphasis.
I don't think
on all
so.
of that,
I mean, I think that's. I mean, that's the. Look, this is the stuff that I find so fascinating. Is that these all of these massive concepts like saving the planet or going to other planets. I mean, it all comes down to these tiny little processes. And I think when you look at it as a huge thing, it becomes insurmountable. As soon as you sort of focus in on, you go, okay, what is my contribution to this is this little narrow corridor here, which again, I think this is why it's kind of such an interesting combination of dealing with people and dealing with science at the same time. So,
and science is fun.
I was going to say, do you find sometimes you just go like, just shut up, I want to do science? Like, is there...
I'm a bit outside of that right now, but I'm looking forward to having experiments back in the lab. I'm looking forward to me being the little girl standing in the control room, looking to the launch pad, seeing BCAL on top of that rocket and knowing that it's going to go to space. Potentially that little girl that stands there in her 60s, looking at the Mars mission actually coming to life. I'm looking very much forward to these things, and I love to think about these concepts and to, develop that and see where we are going. Also love to see how we are now trying to get our inventions and our technology back into industry, to see the products, to see the first quantum products on the market, on a broad market, as opposed to right now where it's a very narrow market. So all these kind of things, I'm super excited about those.
Well, and that sort of almost brings us to the quantum computing stuff, because certainly from a press and tech bro hype side of stuff, quantum computing is pretty exciting. And I've got to say, having seen those giant refrigerators myself and people feeding tiny little fiber optic cables and stuff, it's pretty cool, if somewhat a little, should we say, opaque? or
All right.
Yeah.
So I understand the quantum computing hype. The quantum computing hype, I guess, comes from a point where the why is very readily understood.
Mm-hmm.
So for all the rest, as we started out, right, the discussion as to why do I want to do this and why is this important. And a computer for us is something that is very tangible. I guess everybody on this world has either a smartphone or a computer, or has at least seen one in their lifetime.
Mm-hmm.
So for us, it's very tangible. All of our lives depend on these machines. Mm-hmm. We do everything with them.
That's amazing, isn't it? And how quickly we've adopted them too.
Yes, I mean, if you think about it, and this for me being a German is sort of very poignant. We had a world championship in soccer in 2006 in Germany. I know this is almost 20 years ago, but there were no iPhones.
Mm.
And that feels weird, this huge event and nobody being there with their phones, being able to take photos. So that is super weird that these smartphones there were Blackberries and all these kind of things, but smartphones, they have been around for 20 years and it feels like forever. Yeah. None of us can really remember a time before we had a smartphone, and there was a time, I remember when I got my first normal phone, and that has also been quite a while.
Oh yeah, yeah. Before, I'm so old, I remember before cell phones entirely. So yeah,
Yeah.
we've adopted that technology incredibly quickly,
Super quickly.
for good and for bad. I now spend most of my mornings telling my son to get off his phone, but at the same time, those are skills he needs because that's there are things that are happening in the world. Okay.
Yeah. For good and for bad, for everything. So
sorry, I put you off track. Yeah.
No worries. I veered off track and talked about Mars for 20 minutes.
No, that's fine. Hey, look, anytime you want to go to Mars, just let me know. I'm there. Yeah.
Yeah, let's call Bart and let's go to Mars. So here's the thing. Everybody uses them. And everybody of us who has some technology affinity or has tried to do a more complex simulation or who just likes to play video games has encountered that the power of the computer is not big enough or is not good enough, that the video game in the crucial moment, suddenly your graphics card was not fast enough and you died because of your computer not being fast enough.
That's why I die all the time, Lisa. It's got nothing to do with my playing skills.
No. I could make a really bad Elon joke, but I guess going into the political direction at this point does not make sense.
Yeah, so, fine with me.
Yes, definitely.
Yeah.
David, I know. It's only been the lagging computer. It was the keyboard, it was stuck.
Yeah.
And then the graphics card was overloaded. It's bad. If only you would have had a faster computer.
If only. Yes, but there is always this constant quest to get better. And again, we've got that uncanny valley now where if it's not perfect, our super senses as humans go, that's not a human. Yeah.
So exactly. And so pushing and now comes the promise of quantum computers. And quantum computers promise to be that next step, to be more performant than any of the supercomputers we have. And yes, they are not mainly used for playing games, but mainly for running very complicated simulations, for understanding the weather, for predicting the weather, these kind of things, or for doing intricate computation. Computation is the word I was trying to get to. Computations about some chemical reactions, or you say what it is, and we're probably going to have it too.
Right.
Analyze these huge amounts of data to spot wildfires earlier and stuff like that. That's good, right? It's, as I say, it's not only computing and not only playing and gaming is fun, and it's also good, and there's a lot of money in it. But there's a better, a more valuable chain to it all, right?
Right. A more noble reason for it.
Cause. This is what I tried to say. Okay. Yes, there's a more noble cause to these things. And everybody has run into that problem that they like to have more computer power. And as far as I understand, classical computers are going to come to a limitation at some point. That is because chips cannot get smaller because you've run into the quantum limit.
It's like the line. What is it? They get so close to each other that they start the quantum effects start happening. It's like, don't. Yeah, exactly.
So at some point, that's probably going. We're running into a classical limit as far as I understand. And from that point on, I understand how people with the promise of a more performant computer easily and readily understand the why.
Right.
And if you understand the why, and you have also, you don't have to tell to a huge crowd that they need this. People will easily understand that there's a market immediately. And so now being the first to offer a quantum computer, preferably a personal quantum computer, if you so will, so not a PC, but a PQC, even though that acronym is a little bit used in a different direction in the same anyway, but we're going to come to that. That immediately gets you a huge customer base.
Right.
Without making a lot of efforts about, and this is how it's working, and this is why you need it, and so everybody will understand.
And I guess that's the quantum, that's the encryption thing. Is that just seems to be looming over everyone right now? The idea that it can decrypt. That's the biggest. That seems to be the biggest selling point I'm hearing about it.
Yes, and we can come to that in a second.
I
think it's a bit. No worries. I think it's a bit broader than that. It's just that everybody understands as to why we need a faster, better computer.
Right. So just on the surface, it's like, oh, it's faster. I get it. I want it.
I get it. I want it. I want it now.
Yeah. Okay. I see. Yeah.
And with that promise, with the quantum computing promise of that, I also understand how companies want to be the first to have it. Because if you're the first to have it with a reliable system, there's the big bucks. Everybody will want to have one. Every government will want to have one. Every major university will want to, even though they are big and you saw them yourself, these are massive, huge
giant
machines.
fridges. Yeah.
Yes. Currently, there are other concepts, but usually these are big machines because you need all the cooling and you need it very precise and kind of things. So if you're the first to actually build something that can do these things, you're a winner with a big customer base.
Right. With that first to market, everyone's coming to you. Got it. Yeah.
So I understand the market. I fully understand the hype. I have no clue what Lenovo does, the revenue of Lenovo per year, per annum, but I'm sure it's somewhere in the billions. So the market potential is huge.
Right.
Now, in addition to that, you have this threat that you just talked about, the threat of the quantum computer basically being the one who can decrypt, which is, again, it's just computing power, the one that can decrypt messages or crack codes more easily. And this is the biggest promise or the biggest threat that they pose. And
this is the Y2K of
yeah. And this is why countries are so interested. If you are the first country to have a quantum computer that can crack any code, you are really ahead of all the other nations.
You're reading everybody's mail.
You're reading everybody's mail. There is the Enigma movie with Benedict Cumberbatch.
Oh, yeah.
And you can see how much they invested back then to get that little bit of an advantage. And so the quantum computer promises that same thing. And potentially in these times that we find ourselves in right now, this might be a big advantage, or we might be in a similar situation, without trying to be doom and gloom here. We might find ourselves in a similar situation where this advantage of being able to crack a code is of huge geopolitical relevance.
Well, especially while there's trade wars going on. I mean,
trade wars.
That's the very reason for this stuff, is wanting to know what people are doing and being first to market. Yeah.
Trade wars, there's oil going from here to there, there's ships suddenly being stranded somewhere and you don't know whom they belong to, so whatever, right?
Communications channels, I guess, that'll be...
Communication channels, whatever. Like,
it is a Y2K. It's literally like the Y2K. I remember, it was the same thing. Banks and everyone was running to the banks to get money in case the system collapsed, and right.
There you go. It is exactly that. To gain that little bit of advantage, and in this current climate, and I don't know if this is politically intelligent or anything, but you could say I want to have that little bit of advantage over Russian.
I'm with you. Yeah.
Adversary, right?
Yeah. Who doesn't?
And this is why you have a lot of, in addition to the companies having an interest, you now also have a governmental interest who pours money into these things.
Yeah. What is the Stargate thing that they're talking about? It's like something billions, $50 billion or something they're talking about putting into the new AI thing. They called it Stargate, which I think is hilarious.
That's hilarious. I have not seen that.
Oh no, they've announced a new initiative that I can't remember. Someone will tell me, but they've called it Stargate, which of course immediately I'm like, what?
Me?
but it's an AI initiative to get America ahead on this stuff, and it's a huge amount of money. I'm sure someone in the chat will find it for us, but
Yeah, there you go. And so I guess this combination leads to this kind of explosion that we're seeing, because if there's governmental interest and you have government money, then you also have a reliable customer who's happy to pour in some early money to that. So this is where we find ourselves. So I fully understand the hype. Here comes the catch. This particular application, I think, is the most promising application for quantum computers. Quantum computers are going to excel at decoding text messages. This is what they can do. There are other applications where I think the hype might be a little bit overrated.
Like what? What areas are you thinking?
I've heard somebody talking about big data and data analyses. And I don't think that quantum computers can necessarily help there. But that might be a fault of mine. That might be, I might be too short-sighted. But
what's the pitch, though? Have you heard sort of their pitch on it? Like, what's their take on how this would help? Is it just because they can process larger amounts of information at the same time, or what's the...
I think I think what happens there is that you have a group of people who have this issue that they want to analyze more data faster.
Yeah.
And so what they're trying to do is to have more computers that are faster.
Hmm.
And now the quantum computer promises to be a faster computer.
At certain
and by
things.
That, yeah. And the at certain things for a while might or might not have been something that was communicated.
Hmm. Ha, interesting.
And this might be my very, very limited view, and maybe I'm wrong, and I hope to be wrong as so often. I hope that I have a limited view and that things are completely different. And so I don't think that, from my point of view, I don't think analyzing big data with quantum computers is really where they will shine. I guess they will shine in situations where you have
decryption, though, is a big one unto itself. I mean that's a reason for them to be around at this point, anyways. I suppose. What about? Oh, sorry. If you,
yeah. So anything that is code based, I guess they are going to be good at. So any simulation.
And of course, simulating a quantum world is going to be better than our poor old computers.
Or even a classical thing, yes. Anything that undergoes any sort of restriction, and you just simulate that. Could be, as I said, could be weather models, could be molecules interacting and electrons being shared, and the orbital models and stuff like that. I understand that there are some problems in mathematics that cannot be solved. So all these kind of things where you have a code where you say, please solve this problem, essentially. I understand these codes are usually like, back in the day when I programmed myself, my codes were also really long. I understand that these are several pages long codes, and you don't tell them, do this, please. This is, I think, where they're going to excel at. And of course, there's also a whole branch right now, because you talked about AI.
Of course,
that is looking into.
But is it good for AI? Is it useful for that?
I mean, if I take the things I said, I would say yes, because AI again is a line-based, code-based testing.
Yeah, it's true.
It's a pattern. It's not big data analysis.
But I guess that's why there's Xanadu.ai. I suppose that makes sense. I mean,
yeah.
Oh, I will say this, just jumping in on the coding thing for a second. One of the things that I really liked about both IBM and now Xanadu is that there's a section on their website where you can learn about this stuff. So I actually wrote I used their Python tutorial to write a Hello World quantum computing program, which was so satisfying and did nothing. But at least it was just wonderful to work through it, and I was using ChatGPT and saying, explain this, what is this equation? And I mean, it's a really fun process for someone who just wants to feel like they've, just even if they just want to flex a little about their,
In the end, I expect if we're talking about a personal quantum computer or anything that is integrated into the existing world of high performance computing, so even if we are claiming that it's going to stay a high performance computer and you have these centers, I expect that at some point you will have to have a quantum Windows. You will have to have a usable graphics.
OSQ, yeah.
Yes, OSQ, something like that. Some quantum GUI to have a user interface.
Well, and these tutorials are actually pretty good at that in a way anyways, in that they're using Python, which is fairly, for most nerds, it's not that difficult to get your head around.
I'm saying yes, and I have never touched Python. I've done
some really?
C++. No,
it's so much
fun.
I
went out of programming a couple of years ago and never went back.
I'll tell you, I mean, not that you've got any time for this stuff, but I'll tell you the thing that I love about, well, it's not just Python. I guess it's any programming language, but I've been using Python because it's just so many packages out there that do basically anything. So what I'm finding, I'm using like ChatGPT or a Copilot or whatever, but basically ChatGPT is the one I've been using. And just getting it to do little scripts that do things for me that I wouldn't do, because you might as well just cut and paste 50 times is faster than trying to figure out how to write a program that you don't do every day. This basically removes that part and allows you to write little scripts that could do. So it's just great for helping out with getting things done during the day, honestly. That's myself.
Yes. And I heard that about ChatGPT. To be used as a
Are you not using it? You haven't used it?
No.
Lisa.
No.
I think you need to.
I probably should.
Well, I just think that you, of all people, would have a better perspective on this stuff, and I think it can be useful, even just in the day-to-day, just helping out with some of the grunt work, like summarizing things or formatting things and stuff. That's all. That's my pitch for it, anyways. Although there's privacy issues, I suppose.
If you allow me to veer off of that for a second.
Please. Yeah.
There's a huge discussion going on whether how to make sure that students in universities and schools don't use ChatGPT. And I'm like, please teach them how to. Make them use ChatGPT. But then don't give them the homework to write an essay about the favorite, I don't know, author of the English teacher.
Yeah.
But to make the homework that ChatGPT writes that for them, but that they have to check for biases, for incorrect, for correctness, for completeness, maybe have them amend their own thoughts. Make them use it. Do the opposite.
Yes, because they're going to use it anyways.
And after they leave university or school or whatever, they are expected to use it. As you say, you just told me that I should use it for my day-to-day life. And you're probably correct. But we expect people with a certain education to use these things and use them responsibly and correctly and understand where the report might go wrong or where there's inaccuracies or biases in that report. So please teach children or young adults, whatever you have, how to use it as opposed to trying to stop them from using it, because you will not be able to stop them from using it.
And this is the frustration. I mean, we see this in so many things with like AI's complaint is that, it's going to replace writers and animators and this and that. And I was like, yeah, no, it totally will. It'll replace bad ones. Because the reality is, if you're just churning out mindless television, then yes, AI can do that. If you just want, what's being done before, fantastic. It's great for that. But the whole thing, I did a bunch of T-shirts that say human or say either human intelligence or organic intelligence, because my whole obsession is this is a tool. We got to stop focusing on the tool. I don't care whether a film was made in AI or not. I care if it's a good film. And until now, I haven't seen a good AI film. I want to see a film and go, ooh, that was cool. How did they make that? AI? You know what I mean? Like, that's what I don't, it's not about the AI. It's about what you deliver. And the kid stuff, student stuff, again, I agree. I feel like if this is going to help them get what's in their head out into the world, then I think it should be absolutely embraced. The people who are going to be concerned are people who are bad teachers who are putting out the same stuff every year that can easily be replicated. I'm absolutely with you on that. Absolutely with you.
Make them understand how to use it. If you give them a hammer, they are going to use the hammer. But if you don't teach them how to use the hammer, they are going to injure themselves. And this is where I think the life is important, because there is bias inherent, even racial bias in ChatGPT, because it learns from a racially biased human race.
Yeah.
It's just what I mean, I can hate that all day long. I can go out there and protest against racial biases, but I understand that they are there. There's a reality to it. Again, I'm so sorry. Today I'm just making myself, putting myself into a corner where I shouldn't.
No. I think this is, but again, we have to have these discussions, because otherwise you're on one side of it, which is just like the tech bro. It's just another crypto. It's another scheme for get rich quick, which everyone seems to want to do. You have to be on the other side going like, okay, no. How does this integrate with my life? How does this work? How is this more than just a fancy autocorrect? You know what I mean? Like, and I've found it very, very useful for doing things that would have taken me a lot of time before. But at the same time, I don't want it to write my scripts for me. I want to write the script. That's the fun part. You know what I mean? Like, I don't want it to do my art. Well, except that I can't do art, so it's very useful for that too. I mean,
you can do art.
Yeah, But again, to me, the art is the question you're asking the tool. Like, if you're asking AI to create something, you're the one who's putting those connections together and trying to, So, yeah, it's
there we go.
But yeah, you don't want to have a knee-jerk anti-AI or anti-technology response, but at the same time, you got to be smart about it. Yeah, I totally agree. Sorry, I'm just paraphrasing, but yes, I'm so excited that you feel the same way.
Yeah. So let's see how that turns out afterwards. But here we are. So coming back to the quantum stuff.
Oh, that, yes.
Yeah, there was something. I mean, it's just understood technology,
Open
right?
the bag
like,
of squirrels.
Yeah. Open the bag of squirrels, have a look
at
it. Here we go. So, so also this of course is an issue trying to integrate quantum and artificial intelligence.
Right.
And I also think that is a road to go, and that will also, again, because with the AI you have people who want to have more power and more computing power, not necessarily.
Well, both, but yes,
power.
Yeah, I get you.
Both, I don't want to talk about politics. I'm not.
No, I don't.
I'm not qualified to do that. I don't
Science
go there.
is so much more exciting.
Yeah, let's talk science, and then let's take it from there. So they always want more computing power, more things to do that, more elaborate AI technologies to come out and whatnot. And so I see that marriage as a natural one.
That makes sense. Okay,
that makes sense.
Well, that's exciting then. I mean, you could see some huge leaps and bounds in AI then if that can be made to work.
If the promise on quantum computing delivers what quantum as it is promised right now.
Right.
And while I think there are a lot of areas where it will, as I said, code decryption might be one of them. There might be other areas where I'm not that convinced that it will help. And we will see if on which side AI is. And also, as for you and me, I have a phone, I have a laptop, I have a gaming computer at home, if I want to call it that.
What do you got? What are you gaming on, Lisa? Is it old? You got an old one, or you got a fancy new? Are you a total nerd?
I'm not a total nerd, but I bought something which sounded fun and it sounded performant enough, and now I have to do some shameless advertising again. I got myself a Lenovo Legion Go.
Oh, you got the Legion! Oh, I love
it. With the controllers and everything. Now I'm just looking for some jump and run games that I can,
that's
use the
fun.
Controllers for.
So you've got a mobile PC basically.
Yeah.
Sorry, gaming PC.
They market it as a gaming PC. It's not probably most high performance whatever PC, but it does the trick. That
technology. So it's funny little aside here was I actually invested in NVIDIA just before it took off, not because of AI or knowing anything. I just talked to a lot of kids about gaming, and they were all talking about these GPUs that they use, and I was like, oh, I guess that must be. And I ended up picking up some stock for it and doing very well with it, simply because it just happened that the GPUs were very good at the floating points or whatever it is that's needed for the AI stuff as well. So
there you go. There you go.
But the gaming is
well done, very well done, I guess.
Well, I should have. But for every one of those stories, I've got 100 of ones that just failed miserably and lost my shirt. But well, that's such an interesting question. What about for the markets, for stock markets and stuff? Is this something, if you're talking about it's good at numbers, is it something that you think that I'm assuming that they must be interested in this as well?
I'm pretty sure they would be. I'm not a broker myself. I've got no clue about the stock market.
Neither do I, trust me. It's like gambling. It's just gambling. I've
seen some reels that I found funny where he has a chicken and the chicken tells him whether it's going up or down and whether to bet on stuff. And I find that just humorous.
And it's probably just as accurate as the people who tell you what. Yeah, that's my thing. I honestly, I think my thing is just index funds now. As I get older, I get a bunch of whatever the stock market is and leave it at that. But this is not, by the way, this is not financial advice. My God, if you're taking financial advice from this, then you are a disaster, anyways, and you don't deserve your money. Then if you are, then I've got some land to sell you. Yeah.
I've got horses, so.
Do you really?
Yeah, I do.
Oh my gosh!
I've got horses.
Oh.
So and there's the money.
Yeah.
There's even means like some people.
That is an expensive hobby.
Tell me to put money on the side, and then they have the picture of the horse where it lays on the side. It's like this? Is this what you're talking about? And I'm like, yeah, this is what I took from it. So I don't have neither the time nor the money to invest in stocks. So
right.
Here we are. I'm buying horses. They are fun.
There was a wonderful. I worked with horses on sea with Jason a little while back, and so I got to ride a horse. I haven't ridden a horse since I was a kid. My grandparents had horses. They had lame horses, so they would rescue horses from being put down, and they basically just raised them like pets. So horses would wander around my grandparents' crazy cottage place. It was amazing. I'd be talking with my grandmother, and the window would get knocked open by the muzzle of a horse, and the horse would stick its head in, and she would give it a sugar cube and a rub, and then it would disappear again, and without even breaking the conversation we were having. But when I was doing the show, they said the horse wrangler said that apparently indigenous people in America or North America referred to horses as big dogs. They'd never seen them before. And I was like, big dogs? I don't see it. But having hung out with the horses for a while, I'm like, oh my God, they're big dogs. They're totally big dogs. It's the same kind of personalities and attitudes and goofiness, and they're magnificent. I love them. Love them.
Yeah. There you go. Anyway, back from the financial advice to the question of whether...
Yes.
Here's the thing. The little I understand about stock markets is that they are very unpredictable.
Yeah.
So you could potentially run a simulation on what might happen and try to get yourself some
advantage,
future, some foresight, some advantage of some sort. I don't know whether a simulation of that kind would ever be anywhere close to reality. Again, the more things you factor in, like the more things you can put in, the more parameters you can put in, the more complex the simulation gets, the more accurate it probably gets, until a point where you simulate life itself. And again, I would assume that these people want to have more programming power and more computing power and whatever. And so at some point they will also probably want to go for a quantum computer because again, this is where it should be good at, in solving these massive simulations with massive amounts of parameters. Whether that can be done for stock, or whether that is just too chaotic.
Yeah.
Honestly, I have please don't, this is not financial advice. This is just me rambling about where I think quantum computers could be.
There's definitely a tendency with technologies to when they first come out, they're going to do everything, and they're going to wash the dog too. I mean, like they're going to, like everyone's always got it's all, so there's that hype cycle that kicks in. Let me ask you this: quantum computers, you've got them at the Aerospace Center. What is this something that is going to help your work? I mean, is this going to help you get to Mars, do you think, or is it going to help you with your Mars data? Are quantum computers going to be a part of your research going forward?
Oh, difficult to answer. So, for now, the quantum computer in and of itself, probably not that much.
Okay. All right.
Byproduct, however, might. So, you've seen these machines. They need very good thermal systems, for instance. And people want to have stuff smaller and have it more compact and easier to operate. And so a good thermal stabilization system is something that I would like to have for a flight to Mars, or maybe something that is called a photonic integrated circuit, which is smaller optics.
I think that's what they're working on. I think that's what Sanity's working on. Yeah, they're the little chips that react the right way to the light, to the photonics. Yeah, okay, all right. I think that's what, I mean, I could be wrong, but
so things like that could help us miniaturize our sensors for building them to fit into cars or to fit into planes or something like that. So there are technologies that are going to come out of the development of quantum computers that are going to help us in other situations. And even if these are not new technologies that they develop, the sheer idea that there are companies that are building these because there is this hype, so they have a customer on the other side for whom it is worthwhile to develop these things.
Right.
And so they develop certain capabilities and stuff like that that we can then use on the other side.
And the volume makes it more affordable and sort of democratizes it for people. I see. Yeah, that's great. Oh, I see. So it's not useless to you, but at the same time, at this point, you're not going to be using a quantum computer to figure out how to get your sensors to Mars.
No, that's classical computing. That's just it's just rocket science. Why not you?
Love it. I love it. Just see, rocket science sounds easy to me now. To get my head around compared to this freaking quantum stuff, which is just it's like a bad Marvel movie. I can't. It's so completely unintuitive. And yet, the thing that struck me the last time we spoke was you talked about the probabilities, and it's all probabilities, and that's really helped me because I go like, oh, okay, I don't understand. An atom of zipping through a glass when it shouldn't be able to, but I do understand doing the math and going like, well, I mean, there's a chance. You know what I mean? Like that. That really helped me with that. I wonder if we should go to some questions because we've almost. Do you want a glass of water or something? Like you're amazing. You're a machine.
I'm good. I just hope that we didn't veer off just completely and nobody is now interested in what we talked about. So
well, I am, so I don't care. How's that?
All right, here we are.
This is the beautiful thing about these. I swear to God, I started doing these just for me. If anyone's interested, fantastic. I'm always amazed that people are, and I'm very appreciative. But yeah, we should maybe hit some questions. I'm gonna check out. I'm gonna check my email for Agne, and again, Agne, thank you so much for putting this together because this would not. I'm with Genius would not happen without her. And I don't know if Cal is doing the modding for us today, but Cal the Hammer, as I call her.
There you go.
Fantastic at looking after us. Okay, so let me check my email. This is where I turn into an old grandfather looking. Make the magic box work. Here we go.
Now imagine that the magic box does things on probabilities as opposed to determinism. Yeah.
See?
Things get weirder.
Yeah, you went and made it weird. Way to go, Lisa.
I mean, we can talk about communication and
yeah, I do actually want to talk about that.
Yeah.
That's right. I meant to talk about that, the communication side of stuff. Well, maybe just quickly before we dive into questions.
Sure.
Quantum communications, that's a big thing. Yeah. I mean, that's a big use for this stuff. Maybe we could, I know we touched on it last time, but I'd love to get your sense on where we are with that.
Right. So I want to say 5 years ago, if somebody said quantum, the other side almost always heard quantum communication, and then quantum computers came along. So if I say quantum technologies now, everybody hears is quantum computers.
Yeah.
The fun thing is they work on a very similar, on the same basic principle. It's all entanglement. So the spooky interaction at a distance, basically not having a particle defined in its state, but have an overarching wave function that connects two particles to each other. And if one collapses, then the other one has to collapse, not because they communicate, but simply because the wave function collapses between the two. And this is why, this is why
Einstein hated it. I'm with Einstein.
Yes.
Yeah.
Einstein said that God doesn't throw dice, and he hated it all. In communication, the first thing that is important to understand is that there's no information transfer. So communication does not have to do anything with transmitting a message. Quantum communication very much means the distribution of a secure key. And we come to that from the starting point of the quantum computer. So let's start with the Enigma machine. You have the Enigma machine, and you were able to do all sorts of encryption, and then you broke that, and then you did better encryption, and now we have the quantum computer, and you can break this better encryption. And now we need, so to say, the next technology in order to have, again, secure decryption, because even you and I, if we want to do a bank transfer, we prefer that to be secure. We are probably not going to use a quantum key for that, but still, we want that to be as secure as possible. And from the quantum computer, there are two avenues that you can take. The one is post-quantum cryptography, PQC or PQE, post-quantum encryption. And that is the road where you use classical systems and classical computational methods to produce a key that is as secure against a quantum computer as against a normal, regular computer.
This is the belt and suspenders, cover everything approach.
Yeah, exactly. And then the other side to that is to use quantum key distribution, or to use entanglement, basically, to produce a secure key. And there are a couple of different methods of doing that. There is the prepare and measure, where I don't think that you get all of the security in it, but you at least get the randomness. So in the prepare and measure, you have Alice, who is the one who sends the key. Right? You have Alice and Bob. Between the two, you want to produce the key. They want to exchange a message. They want to encrypt that. So between the two, you need to have a key. And Alice sets a sends a photon in a certain polarization, and you use two bases. So you use the say this basis, right?
Okay.
The straight basis or the horizontal basis, however you want to call it, and then you tilt that by 45 degrees, and you get a basis that is shifted towards the first one.
Okay.
And then Bob measures at random in either this basis or this basis, and Alice sends in either this basis or that basis. And then you agree, let's say in this basis, if you have the horizontal basis, if the photon is up, if the polarization is up, you call that a 1, and if the polarization is horizontal, you call that a 0. And only if Bob measures in the same polarization scheme, so polarization turn, as Alice has sent it, they are going to use that for the key, which means you get a lot of measurements that are not used. So
right.
if Alice sends in the standard and Bob measures in the 45 degree tilted one, you don't use that for the key.
Right.
And then you get a series of 1s and 0s, where all you have to exchange is which way both of them have put their the polarization, basically.
But do they still need to exchange that information? Like, I mean, I guess because the problem with the key stuff always is how do you get the key to someone, right? Isn't it? It's that, you know, you still at some point has to tell someone how to decrypt this stuff. Yeah. They're having to share their polarization configuration then? Yeah, only in which basis they measured. They do not. So Alice does not tell Bob in clear speech or in you know, without description, whether the photon was this polarization or that. So whether it was 1 or 0 that she sent out, she's only going to tell Bob, I send it in the 45 degree, and this next one I send in the standard, and then I send it in the standard. Oh wow! So it's changing all the time. You choose that at random. Oh, wow. Okay. For every photon, for every measurement, you choose the basis, and both of them choose the basis at random, basically. Wow. Okay. And then Alice sends a 1 or a 0 in that basis, which is agreed upon. Bob measures the photon, and then you have, both of them have the key. Right. Without talking about the key, right? You're only talking about the overarching things. Right, right. Wow. Now it gets even more complicated, and it's a bit difficult to explain without drawing. I would love to, you know, if we were to sit now in a restaurant together and we would talk about it, I would now have a piece and paper, flat napkins would be flying. Yeah. I would have asked a long time ago. We should get you like a blackboard or something. Like that's not. It's like yeah. You know, when I watch videos in the evening to fall asleep, I usually put them on my phone and I turn the phone around, so I'm trying to explain it in the sense that I don't have to use my hands so that nobody has to watch it. Right, right. While still I'm saying it's a bit tricky. But here we go. Okay. So, this is the so-called prepare and measure. Okay. Now you can use the entanglement. In the entanglement, what happens is you take a source of an entangled photon pair. And an entangled photon pair, one way to produce that is to use a parametric down conversion crystal. What that means is you send a photon into the crystal. Okay. And that photon is not polarized. Okay. So unpolarized going in. Unpolarized going in. Okay. Then you have, or linearly polarized, probably linearly polarized. Okay. Polarized. And then you have the crystal. Mm-hmm. And due to poor random chance of the photon connecting to one of the energy levels in the crystal and bouncing up and down, you produce two photons. Okay. And because you have the linear polarization at the beginning, you have to hit the same polarization, so one of them has to be polarized up and one of them has to be polarized down. Okay. All right. So together they get the original polarization. So you just but you've split it, basically. You split it. Yeah, got it. Now you have a certain probability of these two photons coming out of the crystal. Okay. And if you think of that as cones, so whatever you do basically in physics, everything is a cone. So you have the point of origin, and then it travels out at an angle, and this gives you a cone where you expect to find the photon. Oh, what a pain in the butt. Okay, all right, yep. Now, if you think of these two cones to originate from the same point, what you get is a line
where the two cones meet.
Ah, okay. Yes. Okay.
Yeah,
Yep.
you have these two.
There's that overlap that's going to hit that.
There's the overlap. So you have these cones, and at a certain point, let's have them as two rings, and you have that point and this point.
Right.
If they expand a little, and now I don't have enough fingers to do that. If they expand a little,
we need more fingers. Yeah.
We need more fingers. Yeah. Then you have sort of two lines that are leaving.
Yep.
Which could be in either cone.
Okay.
These photons.
Right, because so you've mixed up the cones. You don't know which cone they're in.
You don't know which cone they're in.
Yeah,
which means you don't know which polarization they have.
Oh, wow.
And the fun thing is they don't know themselves.
And it's because it's split in half, one of them is got to be one and one's got to be the other.
Yeah. And the only thing you know is that they add up to the original polarization of the photon.
Okay.
But now you have these two photons that are connected by a wave function, and it's even better than you only know that one of them has to be one or the other. The thing now is that they are connected by a wave function where neither of them knows. Each of them has a 50% chance of being polarized that way or the other way.
That's the entanglement.
That's the entanglement.
Yeah.
And so you have this wave, this connected wave basically propagating out along these lines.
Yeah.
And now you get the two photons, and now you can manipulate the two photons as long as you don't touch the polarization. That is important.
Right.
Whatever you do, you have to use fibers that keep the polarization. You have to use beam splitters and stuff that keep the polarization. You can do things to them, but you get these two photons. And now you take that source, this entangled source. You have the entangled photons. We generated the entangled photons without me really going into much detail as to what entanglement does and how it works. Now you send them out. And now you send these two entangled photons to Alice and Bob. Okay. And let them measure them. And you again use these two different polarizations. So either the straight one or the tilted one. The photon runs through both sides. The photon runs through the polarization filter, runs to a detector. In the moment that it is detected, the wave function breaks. That one photon has to be, collapses into the one polarization, the other one has to collapse into the other. And now you just have to agree on which one of the ones you take for the key. So do you make the measurement at Bob? Because Alice will know the measurement at Bob. If she measures something, she will know that the other one measures the opposite.
Yeah.
So you just have to agree on one of them. And then the only thing they have to exchange in order to make sure that they measured the same stuff is to again exchange the base. So they again have to tell whether they measured in the standard or in the tilted.
Right.
This is classical information. We don't really care about that information. So they exchange that. They only take the measurements where they both, by chance, measured in the same configuration. And then they note down the key and exchange information.
Wow.
Encrypted with that key.
And is this done automatically, or is this actually like a manual process still? Is this being automated at all?
There are tests that do this. There's tests to space that do this. There's ground-based tests that perform these kind of things. And of course, you then have a computer behind that takes the key that is produced and encrypts the message and sends that to the other one.
Right. Okay.
Alongside with the.
So this is like the random number generator in a way that we were only.
It is
much
a random
more...
number generator. It is in the end. It is a quantum random number generator, and herein lies. So there are a couple of things that make this very much a more secure way. The first one is the randomness. Any random number generator that you produce is only as random as your code is. Yeah. Which means not vary. Right? So if you have a quantum computer, any randomness that is human written or even AI written, any randomness that is written, the quantum computer can somewhat decipher because it follows a certain algorithm. I mean, I know you can tell your computer to produce a random number, but there is an algorithm behind it. I don't know if it's whatever it is. Take the fifth number of this and that. So there is a non-randomness behind it. Whereas from all we understand,
I was going to say, it reminds me of the lava lamps at, I think it's Cloudflare, where they use that for the randomness, the images of that to create a randomness.
Yes.
But even that's not going to be random. Really.
You can use things for trying to generate randomness, But the quantum system has inherent true randomness.
Yeah. It is
truly
random.
It is truly random. That truly randomness comes into where all of this started out, and this is Bell's inequality. And I'm not trying to explain that. We're going to go into really depth, and I will need slides and everything. So we're not going to go into that.
Okay.
There's Bell's inequality.
Right. Okay.
And Bell's inequality was a test on this randomness, basically. And it showed that this is where Einstein had all the issues with. It showed actual true randomness. And another thing that this promises is the so-called no cloning theorem. That means if there is an evil listener, funnily named Eve, who is in this line of sight and just catches the photon out.
Yep.
Eve measures the photon and sends the photon with the same polarization to Alice. Now, the wave function has collapsed sooner than it should. And she sends that photon with the polarization that she measured out to Eve. And in principle, the process should just go on. And there is this semi-protected channel in the end exchanging the bases. So she just has to gain that information, and she should gain the key. However, the no cloning theorem, based also on Bell's inequality, tells you that from the result that you get, the measurements that you get, Alice and Bob separately get, from the randomness of that result, they are able to tell whether or not the wave function collapsed at their side or collapsed earlier than that.
Wow.
Or whether somebody tried to clone the entangled state onto a third party to save it somewhere, and then when the other twos are collapsed, Eve tries to eavesdrop on these things.
So you could test that first.
Yeah.
And then you've got a secure channel. Wow. Okay.
Through the measurement, you know whether or not somebody has listened into your channel.
Wow.
And so you have basically two stages of security in that. You have the actual randomness, which cannot be reproduced by any sort of algorithm. It's not, it's a true randomness of nature. Or at least from everything we understand right now. This is what Bell's inequality has shown in all of the experiments that were tried on Bell's inequality. So there's the Chinese, of course, were first, the so-called Meteor satellite, where they did that to space. And they found that even to space, all of this
still happening.
The inequality holds. And there were experiments by an Austrian group in the Maldives. I think we talked about that last time. But they also saw this true randomness. So all of the experiments that we have performed, we show this true randomness based on Bell's inequality. And then in addition to that, you have this no cloning theorem. So you have the true randomness from all we understand. Maybe somebody very intelligent comes along and tells us that it's not the case. And you have, in addition to that, the no cloning. So you cannot, if somebody tries to catch the code, the key,
they get caught.
They get caught.
So it's a 2-for-1. You get double the security. Yeah.
You get double the security. And now and then you encrypt your message with the key that you've just established, send that to Bob, and Bob decrypts it with that. And for that channel, you can use, again, a medium security channel, so you don't really have to worry because
no one can read it anyway.
There's your super high encryption on top of that, which you have to crack actual randomness.
So it's not speeding up communications. It's just doing a better job of encrypting them and keeping them secure. But is there nothing we can do with that instant collapse of the wave? You don't get faster than light communication because damn it. Wouldn't that be fun though? That would be so cool.
Yeah. There's no information transfer faster than the speed of light.
We still can't break that with this quantum stuff.
No, we can't. We can't. I know it feels like it. And there is a concept which is called quantum radar and quantum LiDAR, where you want to enhance these kind of detection methods using entangled photons. And from all I understand, this works on this principle. So when does it collapse? How far is it away? And so to use that for reconnaissance.
Interesting. Okay.
I'm not sure if I have that right. It's always been a bit on the back burner for me. Like this was, I am aware that these things happen, but it's always been a bit, I never really paid it a lot of attention. there seem to be a lot of limitations to it and distance-wise, and it doesn't seem to be all that applicable to our current means.
Yeah, I've never heard of it, so I'm guessing it's not getting...
No, it's not getting a lot of traction. There's other things that do, but yeah. And of course, if you have these entangled photons that you can distribute, and you have these entangled states that you can distribute, you can now think about connecting to quantum computers.
Right.
So you're not using it for producing you're not using the entanglement to produce a secure key, but to have what we call distributed computing. So you basically have an exchange of the state, and thereby you entangle the two quantum computers on different sides, which is how they work. So each quantum computer has an entanglement of the qubits. This is how you get this faster computer power. And if you have principle, if you connect the second one, you have more of the computing power, and you can do more. So this is distributed computing. And then there's something which is called distributed sensing, where you're trying to connect, say, optical clocks by entangled photons to enhance the performance of those. This goes a bit beyond that, and we are very far away from that at this moment in time, as far as I understand that, from these quantum networks and distributed computing, distributed sensing, all these kind of things. There are people thinking about that and how to establish that. But no, you cannot have faster communication. You can just have more secure, which is
great, which is fantastic. I just
already that
the sci-fi nerd in me just loves the idea of beating that whole faster than light thing. But I get it. That does make more sense. It's funny when you talk about the idea of a distributed computing. I believe that the Xanadu folks are working on a modular quantum computer that would allow that kind of communication between them all. So I guess we should go to questions. I could talk to you forever, but I feel bad because I feel like I'm selfishly stealing you all to myself. Okay. Martin Taichi asks, what quantum products are there on the market? And there are a few.
Oh, there are a few. This depends on what we are calling quantum. There is an argument to be made to call a transistor quantum, and if I call a transistor quantum, then there's quantum galore, right?
Right.
We're not going to do that. We can call lasers quantum. And also then, I mean, it's in principle, yes, it is all the states, and you need the Schrödinger's equation to understand that, and excitement of the atoms, and deexcitement, and, the admittance of photons, and so on and so forth, and the resonator, all these kind of things. You could call a laser quantum, but that's not what he's asking. I know that that's not what he's asking. Okay. There's also something which is called the second quantum revolution, and usually people talk about entangled systems for that kind of thing. I think there is something like a quantum random number generator on the market. I'm not entirely sure.
Seems to make sense. I feel like that's something you should be. I mean, that's perfect for it. Yeah?
And it's not very difficult. So I mean, it's you have to build it, and you have to have the single photon detectors, which are probably the biggest thing in it. The most expensive thing, the most difficult thing to have.
That's the fridge part, isn't it? Isn't that the fridge part of the whole thing?
That's the fridge part. The fridge part of the quantum computer is also to keep the entangled states and to keep it in the ground state. There's all kinds of things to do. But yes, this is also a fridge part. This is where it gets a bit more complicated, but in principle, yes, quantum random number generators are something that I'm sure we will see. But what the question alludes to is actual other systems. So clocks are one of them. There are, of course, the clocks on Galileo, which are available right now, and I would like to call them. And there are tons of quartzes and stuff that you can buy. But currently there are a handful of companies that are looking into cold atom systems or cooled atom systems to build clocks. In the US, examples might be Vector Atomic or AOSense or Spectral Dynamic or Cold Quanta Inflection. Somebody's going to get angry at me that I didn't mention that. In France, there's Exail or the old Muke ones. So not old, it was Muke ones, then they got bored, and now they are Exail. So there are a couple of companies, and let's just mention the Australian Nomad Atomics, and I'm sure I've forgotten people, and they're going to get angry at me.
But the advantage of a faster clock is that it's better for things like geolocating and all that kind of stuff. Like the faster you've got, the more precise your measurements could be, I'm guessing. Is that?
They are not necessarily faster. It's just that if you cool the atoms or there are other ways to doing that, but basically if you cool the atoms, you have less distortion in the signal, and so the signal stability gets better.
Oh, okay.
And the accuracy gets better.
Okay.
The bandwidth of the states gets lower,
and
you get a higher accuracy, basically. Higher accuracy
less
and higher
drift
stability.
as you...
Yeah, less drift, and also in the beginning, so even at 1 second, you get a more accurate signal with a lower error on it. And the lower the error, so for instance, if you want to do georeferencing and you go to a mountain, the lower the error on the height that you're trying to get, the lower the error on the position in navigation, the lower the error on financial marketing when you want to buy or sell stuff. Any timing service. Really.
So quantum random number generators, got it, and quantum clocks, got it. Okay.
Quantum clocks is something that you can buy right now. I've got no clue what they cost. If you want a cold atom system, you're probably looking at $500,000, but that's just a random.
I'm okay. So. I've got I use the phone.
You got it?
I use the phone for my time. It's fine. Yeah.
It's fine. That also depends on that also relies on a quantum clock, by the way. Probably a cesium clock somewhere, and GNSS. And then you get your signal through the mobile phone network, and
so that's kind of quantum too, anyways.
Yeah. So the more accurate those are, the more accurate the time on your mobile phone.
I'm late for everything anyways, so it's fun.
Yeah, I know, me too. I'm thinking in half hours, not in minutes or seconds.
Yeah, exactly. Yeah.
Not even talking about 10 to the minus.
I'm thinking in mornings or afternoons. That's basically where I'm at. Yeah.
Next meeting, whatever. Yeah. Bright, dark, whatever. So yes, so these things you can buy. You can buy quantum gravimeters and quantum gravimeters. You can buy, and you can buy.
And that's for sensing changes in gravity.
Yes.
Okay.
Right. So you have these systems. These are about half a meter high currently. If you want to buy them right now, probably around half a meter high, and you put them somewhere, and then you measure the underlying gravitational field to see whether there's water or whether there is prospection, so gold or any oil, whatever you want to see. You could also use that in civil engineering if you wanted to know whether there's. So we had that in Germany probably 20 years ago, where they're building something and there was a massive hole underneath, and so everything collapsed because the structural integrity was no longer given. And then in Germany you also have a problem, with bombs from the Second World War. So,
of course, the UXBs, right? Of course. Yeah.
So these things are things that you could detect with that for civil engineering, for instance.
And this one system can detect many different types of things that they're seeing, or are there specific ones for oil and specific one for minerals, or?
What they see is a gravitational field. There has to be some type of intelligence, could be AI, don't care, but there has to be some kind of an intelligence behind it to tell it the anomaly you're seeing is probably iron.
Okay, right.
And there's a big thing there because you have to know something about your surrounding. People get very angry when I say that because I think they misunderstand me. So if you know that you have a sand underground and you measure something, then you can say, it's either this very heavy compound, which is super far down, or it's this less heavy compound, which is super close to my detector, because I only measure a gravitational signal, and it can be caused by different things. So you have to know a little bit about your surrounding and what you might expect. So do I expect, if I'm in the Sahara Desert and I'm looking for water, what would that look like? Yes, I can think about it. Okay, so it's probably further down, and it's probably like this. So then I can look for that kind of signal.
So it's not as simple as like a lookup table of this is the reading you get if you see water. There's different things that can affect that. I see. Okay.
You have to do some simulations and you have to do some thinking about what it is. It's not necessarily quantum thinking because you have the quantum system there. It's more of a geological, geophysical thinking. Like, what's the surrounding? What do I expect to see? What would a certain body look like that I'm looking for?
Right. Okay.
The big advantage of these quantum systems is that they're drift-free, so you can check today and then you can check tomorrow. And if the system looks different, then you know very well what's going on and you don't have to think about it too much because there's no drift in the system, so you have an absolute measurement now.
Oh, interesting. So you would know that that's water because it's a different reading or whatever.
It went away, or somebody did some, or you would know.
Could you interact with things? I mean, could you sort of pump things into the ground to figure out what that reading?
Potentially.
Yeah.
Yeah. So if you were to look for a hole, say, for a civil engineering, right? If you were to look for a hole or for whether the ground would be stable enough to build on, you could measure one day and then you pump in water or concrete or whatever you want to do, and you would see how that would distribute. Like if it and again, you would need a civil engineer there or
right to tell you what you're looking at.
Tell me what that would be looking like. If it's if there's a cave, what would that expect? What would you expect? And if it's not there, like how would you expect the fluid to distribute? Stuff like that.
It's not like one of those stud finders. It's not as clear as like, yep, there's the stud.
Yeah, but even that one only measures a magnetic field or a electric field, and it's programmed into it that you expect a wall, and you expect to have these rods which are very close to the outside of the wall. So if you see this kind of field, then this is what it is, because you know very well what you're expecting.
Right, yeah.
So it's actually a good example. This is how it would work, because you know very well what you're expecting, so that would work the exact same way.
No, that's great. That's interesting. So really, the more information you've got about whatever you're trying to measure, the makeup of it is going to help as well. So it's not, as always, it's not one tool will rule them all. It's a series of other ones that allow a more accurate reading from these tools. That's great. What about things like MRI or the monitors that are using these quantum dots and things?
Yeah. Oh, quantum dots are a fun thing to do.
They're really cool.
They are really cool. They're really cool. So magnetometers are something that you can also get commercially. There's at least 2 American companies that sell them right now, also at a more reasonable cost.
Just detecting magnetic fields?
Just detecting magnetic fields. It's quantum systems are super susceptible to outside forces. This is why we had them in laboratories for a long time, where we protected them, and we had this one PhD student who could operate them because we were at a stage where we
You were that PhD student, were you?
Yeah. No, I was a PhD student in plasma physics.
Oh, okay.
And you needed that, and it I don't know, the moon needed to be in Capricorn, and
that's right.
Needed to have rained the day before.
The goat needs to be sacrificed before that. Yeah, exactly. Yeah. It's like the early days of computing. Yeah.
And then you would get a measurement of quantum mechanics to understand what's happening.
Right.
And right now we are seeing this, and I have a lot of presentations that look like that, where I say, yes, that was a bug, and then we take that bug and we tell it's a feature, because nowadays we understand how the quantum system works in and of itself. So for instance, how so a magnetometer would usually be based off of a nitrogen vacancy cell in diamond, an NV center in diamond, or a color center in diamond.
I love the way you just sort of trip that out at the top of your head. That's amazing. Yeah.
Right. No, of course. What you do is you take a diamond and you take out very elegantly, very well. They do it very well. This is the only way I can explain to you how the process is done technology, because I don't know. They take out one carbon, they put in one nitrogen.
Wow.
And now what happens is that if you look at the periodic table, nitrogen and carbon are not on top of each other, but next to each other, which means that nitrogen has an electron fewer than carbon has, which means that it cannot take all the bonds that the carbon had before. And that creates a vacancy center. Because there's one connection left open.
Who's not doing their job. Right, got it.
Who's not doing your job.
Yeah.
So this is why you have a nitrogen vacancy center. This is where the name comes from, an NV center, or a color center, basically. It's also called a color center because you can then shine light into it, and it does weird things. And we understand how that works, but these systems are super susceptible to magnetic fields. So you just probe that, and if the response of the crystal changes, you know that the magnetic field changed. And you can again do the same thing. You can use that as a Hall sensor. You can use that to detect magnetic fields and so on and so forth. And these NV sensors are something that are commercially available at this moment in time.
So it can pick up. And how sensitive are these things? I mean, are you picking up you picking up bugs thinking? I mean, what's the
Yes. So depending, there's optically pumped system, which are usually warm vapor cells. That's a tricky word in German. You want to always call that warm vapor cells, and you want never to call that gas cells. So it's a warm vapor cell.
Warm vapor
sorry.
cell. Very good.
No,
okay.
warm vapor cell. I'm putting
Okay.
myself into a corner where I really shouldn't be. Warm vapor cell. I'm just trying to avoid these things. Let me just quickly do some. No. I want the VVE surveillance. Warm vapor cells. It's basically, so what that tells you is that it's at room temperature. That's why it's warm, and you have some vapor inside of it, some kind of gas inside of it. Usually rubidium, because rubidium is super easy. Everything's based off of rubidium. You have all the lasers for rubidium. You can have superconducting interference devices, which also works quite nicely. There are some different types of sensors that you can use. You can also use so-called Rydberg atoms. A Rydberg atom is an atom where you have all the electrons in the normal shells, if you want to go to Bohr's model, which is not that nice from quantum mechanical point of view. And then you've got one electron, which is super far out.
Okay.
And it orbits on a really elliptical, far out orbit.
Yeah.
And that's called a Rydberg atom, and they are super sensitive to all these kind of things.
Because it's so far away, you could sense it being knocked off course or whatever.
Yeah,
okay.
exactly.
Right,
exactly.
Okay.
There's an additional, so there's something that is called the Zeeman effect. So these energy levels that are calculated through Schrödinger's equation for every molecule, every atom. If you put in more energy, for instance, through a magnetic field, you split them. So it's not only that you change the energy level, but you also gain more levels.
Huh.
And that's called the Zeeman splitting. Then you get all kinds of intricate things with that due to the electric field caused by the electron orbiting the core, and due to the proton in the core orbiting itself, and so
you're picking up. You're literally able to pick up that kind of level of.
Yeah. That's what you do with the clocks. You probe fine structure or hyperfine structure. These are called components. However, an external magnetic field will do a Zeeman splitting, and you just probe that. And that gives you the accuracy of the sensor. And basically what you get, so a Hall sensor typically is able to detect a millitesla. And Tesla for me is a very weird kind of unit, because I never know. I have no feel for a Tesla. But that can typically do a millitesla. The NV centers, the color centers in diamond, are typically able to do a picotesla. So I even have a cheat sheet for me to do that. So that is 1, 2, 3, 4 orders of magnitude down from the milli.
Okay. Right. But I just can't get over how precise these are anyways. I mean,
4 times 12 orders of magnitude down, right? So it's
wow.
10 to the minus 3 to 10 to the minus 12 from milli to pico. And because that's always 1,000. Milli to micro is 1,000, micro to nano is 1,000, nano to pico.
I always get that wrong. Yeah, I've
got a cheat sheet.
The cheat sheet's genius. I'm stealing that for sure. Absolutely. I want a cheat sheet too.
I took a cheat sheet from Wikipedia. I just got it here.
Yeah.
And then the superconducting interference devices and the warm vapor cells are somewhere in the femtotesla, which is another 3 orders of magnitude down from the pico.
Wow. I mean, that level of sensing is just, I can't get my head around it. I mean, I feel like if you thought too hard nearby, you'd throw it off.
Yes. And so this is where they are also used for. So you can use them for brainwave or brain activities to measure electric fields in the brain.
In a non-invasive way? Like you can stick them on your head instead of in your head?
On.
Oh, wow.
Stick it on.
Oh, that's interesting. So that could be instead of these horrific drilling and poking holes in the brain. Wow. Okay.
Again, depending on what you're looking for and how precise and how much overlaying signal you have. I'm not a physician. Isn't that what? I'm
not a doctor, damn it.
Yeah, well, I'm not a doctor. I'm just a quantum physicist.
What do you want from me? Yeah.
What do you want from me?
Exactly.
Yeah. I'm so sorry again with the reference to the wrong kind of universe.
Not at all. Not at all. No. You kidding? It's my universe too. TNG was my real. I grew up with that. That was my baby.
Yeah. I can't get over my love for Kirk. It's a bit, we are TNGs. But anyway, moving on. I told you what. I didn't tell the others that the Mars mission is called Maquis. And so
I know.
There we go.
I love it.
I'm deep in the Trek
you
universe.
Nerd.
Mad.
Yeah,
Yes.
yeah.
I'm sorry. Yes, I am. I know I don't.
We're never going to get through all of our questions, I realize.
No, we never. But
which means we get to do another one.
Yeah, but magnetometers you can also buy, which means if there's some kind of sensor that you're looking for, probably there's a quantum company selling these, and these newer ones are also sold. This is what I'm trying to say. Yes.
Next time we should totally talk about the quantum dot thing, because that stuff's fascinating as well. Just absolutely.
Next time.
Yeah. If I could.
All right.
We're never. Yeah. I think, you know what it is? It's the entanglement. I think we're entangled now. Aaron Bell says, how long do you think before quantum computing becomes accessible and affordable to the ordinary consumer? If it does, for that matter.
I think it is.
Yeah. You think it is?
I think it is. Maybe not to the extent that you would want it to be, but as you said, you also were able to do this Hello World kind of thing on it.
Oh, yeah.
And I think I think IBM also has a portal where you can.
Yep, IBM has a great one too. Yeah. Just because I was just there, I'll point people at Xanadu. Xanadu.
So I think there are some things where you can do quantum computing as a regular person. If you want to do that for any extended sort of simulation, more complex problem, you probably would have to pay for that depending on what you want to do with it.
Mm-hmm.
But that's as normal high-performance computing.
So it's going to be the same sort of thing where you can log into someone else's quantum computer, which is what I think they're all doing that. I think IBM's doing that.
They're all doing that.
Yeah.
They're all doing that, and I think they all have these kind of, as you said, these kind of sandbox systems where you can just log onto the web page and just try yourself
There's also
out.
emulators as well. It sort of emulates a quantum computer, so you get to do your quantum computer coding, but it's not actually on a quantum computer, but it's a quantum computer-ish, if that makes sense.
Yeah. There are things like that.
I don't think they let me program on the quantum computer. I'm pretty sure that was probably an emulator. I don't imagine they. Oops, sorry.
I don't know.
Yeah.
In the end, you can't really do. I mean, probably you can't do much harm unless you're there with a huge axe or a.
Well, give me a chance. I was terrified of tripping and falling, or drop.
I mean, Douglas Adams is a wonderful fountain of wisdom, and he said people who claim something is foolproof usually underestimate the ingenuity of fools. So
that's so true. Oh my God, I've got to read his stuff again. I remember loving Hitchhiker's Guide and all the ensuing books. Yeah.
If you get the time, and I know I'm veering off and then we're coming back, I promise. If you've got the time, there is a video online of him, which is The Parrot, the Something, and the Something of UCLA, which is about an hour and a half long, and he just talks about random stuff.
Oh, fantastic.
So that's,
I'm looking that up now.
That's if I want to calm down and do. I usually listen to that because it's just very calming to my mind. I enjoy the story that he tells.
Yeah, he's an amazing guy, wasn't he?
But to answer the question, when there will be a quantum computer in your home, in your cellar, or even a quantum laptop, if you ask me, it's never, because I don't see the reduction in size. I don't see the miniaturization process. I hope I'm wrong.
Right.
I really sincerely hope I'm wrong. I hope they figure something out based on NV centers as well. So these NV centers and diamonds are a thing. If you want to do a quantum system, if you have a problem and you want to solve that somehow, throwing an NV center on it is usually a good idea. And they also work as sources for entangled photons, and thus they also work as qubits. And you can have multiple NV centers in one crystal. And so you can build a board and entangle these different NV color centers,
right,
which are single atom centers. And then each of them acts as a qubit. And so you can have a rather large qubit system as far as I
How big have they got with those? How many qubits they got on those now?
I don't know. I'm sorry.
Yeah, sorry. That's not your area of expertise. Yes, got it. Yep.
I'm really sorry. I don't know where they are, and it's difficult to keep them entangled and stuff like that, from what I understand. So you have to keep that at a certain temperature. But I could see a personal quantum computer based off NV centers in Diamond, or if that ever happens, I would expect that this is the system or something similar.
We also don't need it though. Like, in a way, sorry, not to negate your question, Aaron. It was Aaron Bell who asked that, by the way. But the idea that, as long as you can log into a quantum computer, then your laptop is a quantum computer. That's,
Yeah, but we all want to play Baldur's Gate 20 8,500
on my Q4090 or whatever exactly.
On the Q4090, and we don't want to die because it's lagging. So we definitely want the one qubit more than the other one has.
It's true. And that does seem to be changing very rapidly. I think that's part of this modular thing that Xanadu's doing is that, by the way, Xanadu is actually named after the ELO song that was in, you're not old enough, but there was a movie that came out called Xanadu that had Olivia Newton-John in it, and I went to see it in the theater, and it was terrible.
There you go.
And it was terrible. Yeah. But I still love Olivia Newton-John. And and the song by the Electric Light Orchestra was Xanadu, and that's what they've named this.
That's what it is. There you go. We are all nerds at heart. But yes, so this is maybe the answer to the question. So yes, I can. If there's demand, I guess at some point we.
But miniaturization and getting those fridges smaller is going to be a difficult task. Yeah. All right, Sylvia asks, Lisa, it's getting personal right away. Do you think the future of cybersecurity will be in the hands of quantum computers, or will we still need the human element?
Well, I think the quantum computer and the human element are not separate from each other. You will still have to write somehow the algorithms unless you're using AI. And this is where I guess a problem that also robot people have.
Those robot people.
Necessarily.
Yeah.
Yeah, the people, I don't know how to call them. Robot scientists, robotics.
Yeah, I guess would they be roboticists or mechatronics?
Roboticists, whatever. Robots are very often mistaken for having inherent AI, and that is not true. You can have AI without the robot, and you can have the robot without the AI.
Yeah, absolutely, yeah.
And the same is true for the quantum computer. You can totally have the quantum computer with a human element who programs the thing, and you can do what you talked about before, where you have AI put into it to program it. As long as you don't put the AI into it, it will not do anything unless you have a human sitting in front of it programming it. So quantum technologies and quantum computers are more of a tool than that they are AI immediately. If I get the question right, maybe I'm getting the question wrong, but I would say that for quantum system to do these cybersecurity things on themselves, you would probably need to implement some sort of AI to run the algorithm, write the algorithm that is then run on the computer. And you also need the message to create somewhere where you need the security for and stuff like that.
Well, and I guess to some extent encryption is kind of an automated process now anyways, isn't it? I mean, the encryption doesn't require the human so much as that we just need the humans to be using it, basically. That's
basically. Yes.
All right, good question, Sylvia. Randy Rogers says, what are the ethical implications of a quantum computer? I'm sorry, I've completely put you in the corner of quantum computing, and I know that's not your...
No worries.
But yeah, ethical
I mean,
ethical
I take this more as a fireside chat, and maybe I shouldn't because I'm putting myself into very dangerous territory. Ethical concern.
Our quantum queen is on fire.
Yeah. I would prefer these discussions to be over a glass of wine.
Yes, it's true, and some really nice cheese. I'm a big cheese fan.
Some cheese.
Oh, good cheese.
Anyway,
is the best. Yeah, sorry.
No, let's not go there. Yeah. Anyway, lived in France for a while. Love cheese. You cannot get me away from cheese. I love cheese.
Oh my god, and the French cheese is the best stuff too. Like,
yeah,
that's insane.
French cheese.
Yeah. I would move there just for the cheese.
Yes, it's amazing. So anyway, ethical implications, as per usual, are mainly seen once the bad happens. So if somebody would have asked people who first were able to divide the atom what kind of ethical implications that would have, they probably would not have known. They would have said, yeah, maybe clean energy. Who knows, right?
Well, or end a war was kind of it, wasn't it?
I mean, yeah. Yes. But they then developed it very clearly with that implication, with that thing in mind. So to get to the ethical implications of it is a bit tricky, again, because quantum computing and quantum technologies as a whole is more an end to a means. So a means to an end, the other way around, sorry, again, my English. A means to an end. So it's like a normal computer. It's more performant, and it will probably get you quicker or better to a problem, to a solution to a problem that you originally put in. If the problem you put in is one of ethical consequence, then yes. But for me to understand what kind of problems people would put into computers, I would have to be a scientist of so many fields that I don't know.
Maybe so it's just going to be faster at making good. It's going to be faster at doing good and also faster at doing bad, basically.
If you, I don't know, if your scheme is how can I rob every bank in the world and be as fast as as Father Christmas about it, then yes, probably that is for the bad.
Are there environmental concerns? I mean, is there any, like, does it use a massive amount of power or anything? Does it have any of those kind of issues?
It does. That is a good question. It does. So the amount of power that it uses, you've seen the fridges. The amount of power that it uses is definitely an issue. And I've heard about initiatives to reduce that kind of power power requirement. I guess it's similar for Bitcoin, where this is also
it was a huge issue.
Concern.
Yeah.
So these are issues, definitely. It uses power. The development uses a lot of power. You have all these people who need to eat and feed and do all kinds of things and travel around the world, and you build buildings with concrete. So, yes.
Right.
Yeah,
okay.
Concrete, I think, as far as I understand, is one of the worst climate.
The worst. Yeah.
Yeah. I tell that to myself every time when I go on a plane, and then I don't think too hard about us trying to build a new building right now. So anyway.
Yeah, we got to come up with something better than that too. We better start using. We better start making them out of like plastic recycled, blocks of some sort. Okay. So good. Good response. That's a good answer to the ethical implications. I think that's good.
I don't know.
It's a hard one. Martin's got another question. I would like to know how you liked the movie Martian from the view of a scientist.
I loved The Martian.
Yeah, so did I.
And let me tell you why. So a lot of the movies, there's one scene in The Martian that I didn't like. And by the way, I love Andy Weir.
Isn't he great?
Have you read Hail Mary?
No, I haven't.
It is. Oh, go! Please do.
Okay,
please
I will.
Do.
I will for sure. Okay.
It's amazing. Artemis, from my point of view, not that strong, but Hail Mary, amazing. So why do I like The Martian? The Martian was sort of honest to me.
Yeah.
The plot was not based off some random idea that I didn't believe. It was not people putting themselves unnecessarily in danger. It was all very well thought out. They took in all the things that were relevant, which I understand is very much what Andy Weir does, and like the lagging in the time between Earth and Mars and stuff like that. And I really liked it. I also saw how, as a scientist, you would start to think, okay, so I've got this problem. I need a solution. Where do I start? Right, I've got this human waste, so let's start with that. I'm a botanist, so I'm going to use my tools in my toolkit shed in order to do these things. So I loved that movie. I really did. I afterwards heard the audiobook, which I, of course, preferred. But yes, so...
I read the book, too. I loved the book as well.
There's one scene in the movie which I think is made for dramatic effect, where they have to somehow go out of the spaceship to do something. I don't remember what it was. That felt stupid because it felt unnecessary.
Yeah.
This is something that I don't like about movies. A movie that for me falls into the same category is today I'm just doing fireside chat, so here we are.
We need a fire.
A movie that for me falls into the same category, even though it's a bit older, is Ex Machina.
Oh.
Which, I mean, it's the premise which is bad. I don't believe that anybody could do that in their basement by themselves.
No. But still.
But let's keep that as read and then move on from there. And then I really liked it.
Yeah, that was
I really enjoyed it.
It was so exquisitely made too. Like it's a gorgeous film. Yeah.
It's beautiful. I love it.
Yeah, the sexy robot's a little overdone, but still,
But they explain why they want to do it.
Yeah.
And so I get also that it's not made for purely dramatic effect, and this is why I liked it. But anyway, again, I digress.
Are you a Blade Runner fan? Did you like Blade Runner?
No, here I am. I've not seen it. Agna told me that when the next time we meet, I am obliged to have.
I think you're gonna have to. Yeah, I'm a little disappointed, Lisa. I must say.
Yeah, I know.
No, just I think you. Well, I don't know how that holds up. That was I was like, you looking up at the stars. I was looking at the movie stars. I was in that movie watching it over and over and over again. I just from my own Again, it's nihilistic fantasy sci-fi. But there was some wonderful sort of aspects about these hybrid human computer things. But actually, that's an interesting. What about the organic computing side of stuff? Could you mix organic computing with like the idea of like a thinking machine with quantum computing of some sort? I mean, are there hybrid things going to happen? I mean.
I'm not a biologist. I'm a quantum physicist.
Yeah, but you gotta be, oh, come on. But I know you want to fire viruses through
I do.
Yeah.
So here's the thing. Human brains basically work on the system of entanglement, as far as I understand. This might be one process of how humans think. And if that is true, if this assertion that I just made, a bit rationally, is true, then yes, you could also use biomaterials to use for computing and to entangle that with other hardware systems.
So there you go. You may have taken away my instantaneous quantum communication, but you gave it back to me with the biology stuff. That's great. Okay.
Yeah, but I'm not a biologist. I have no clue. I don't know where that would fall.
But you've given me hope, Lisa. You've given me hope, and that's what I need.
Stay away from squishy things and do more of quantum and hardware and stuff.
I never used to like squishy stuff. I never used to like the squishy sciences, and I've got to say I've really come around to it because I don't know. I don't know what it is, but the silicone stuff has always been my fascination. I mean, you looked up at the stars. I was looking at what computers they were using. I loved all that stuff more than I like the technology more than in a way than the actual astronomy side of it.
Right.
But yeah, that's neat. Okay, sorry, I should go back to the other people's questions. I keep stealing your question time, don't I? And how are you doing for time, by the way? And how are you doing for energy? Because you have been amazing.
I'm not worried.
And we're moving into hour 2 here.
Yes, I know. I feel bad, but don't worry.
Don't feel bad for me. I'm worried about you.
I'm all good.
I don't want to break
you. That the content is what you're looking for. That's all.
You are the content. Okay, what do we got? Sylvia says another maybe silly question. If we ever reach a point where we can simulate life and download ourselves, for example, for retirement, where you can live whatever life you want, would you do it?
Would I do it?
Yeah. Would you be a digital only being if you could? I bet you weren't expecting this question.
No, I was not. I guess. So I would be intrigued. But then, as per usual, when I'm intrigued, I know that there's a television series that I have not watched. But a television series usually tells me that there is a kind of some dangers or something that they're
Black
going to
Mirror?
portray.
Are you talking about Black Mirror?
No, I've watched all of Black Mirror.
Oh, good. Yeah.
No, it's a different. No, there's a different one. I don't remember what that was. It's probably on Amazon Prime. Don't remember.
Okay,
really,
right.
don't pull me to it.
Right.
And then there's the Hamilton books, the Void trilogy. So in case you haven't read that, those might be a good one. Where they're also talking about this and multiplying yourself, and then of course they get into all kinds of fun ideas that you could do if you multiply yourself.
Right.
So it's a good read for everybody over 18. I want to say.
Oh, really? Okay. Right.
Oh yeah, you have no, yeah.
I've never read Hamilton stuff. I don't. Sorry, I might have read something.
The Void trilogy is fun, but it's very definitely over 18 stuff.
It's like my son would say, it's for grown-ups, Dad. You don't want to watch it.
Yeah, it's for grown-ups, Dad. Yeah. So I think the problem here for me is how much would I trust the technology? So
right.
I would definitely not be the guinea pig.
Right. Yeah.
I would not be in the first round. I would want to see whether the technology proves itself and how that works and how it's maintained and how are the servers maintained and how good is the quality of the download and all these kind of things. And then potentially, yes, probably also means how much money does that, there's all kinds of things. And on the other side, while I'm very attached to this life, and maybe I'm just not old enough to feel that yet, but I'm not that big on immortality. So,
I don't want immortality from a physical standpoint, but I'm happy to, if I could just have the brain without all the problems, that'd be kind of fun for me.
Potentially. And maybe it's just because my life still feels immortal to me. So, there might be different things there. It's a bit, I know we talked about a lot of these metaphysical things and less about physics. So I understand where these questions come from. So a big maybe.
A big maybe. Okay, fair enough.
That question.
All right, Lord Vilter.
Depends.
Oh, sorry, you got more. Sorry.
No. It depends was all that I wanted to add. Yeah, go ahead.
Right. So you need to know more before you could decide whether you're going to be downloading your consciousness. Yeah. Okay. Lord Vilter asks, what do you guys think about remotely building on the moon or Mars? You think laser satellites can bring down the latency enough for it to be feasible to remote control excavators and construction drones? Not entirely a quantum question, but
no, not entirely. There's a lot of bias to that. So I guess in the end, the trick to building on the moon, if we really wanted to, and I guess there's less of a science-driven idea there, and more potentially first a science station, which I would assume is remotely controlled, and the speed of light is the speed of light. So optical communication, yes to that, which is a good thing. And that's fun, and people are working on it, and DLR is working on that, so that's amazing, and that works great. And you would just have to think about. So the big issue you get is even if you take a laser, you have a certain widening of the laser,
right?
And so you have a lot of signal loss,
like the quantums.
Like the quantums.
There you go. Yep. Okay.
And in the quantums, it's always worse because you have single photons. There you can send as many photons as you like.
Right.
But you still get the
cone.
You have the huge distance, you have the cone, and so you have a lot of signal loss. But you have that with radio waves as well, so it doesn't really get all that much better. You just need the antennas for it, or the optical.
So there's always going to be a lag of some sort.
So the lag, definitely, because you only have speed of light to communicate. And the other one is signal loss and signal intensity, which is signal quality, really, in the end. So you have quality and lag.
Okay.
The lag, the speed of light is the speed of light. There's no way around it. And that's the same. So that's the same for radio or optical.
Right.
You still have the speed of light. It's just the amount of data that you can send, which can be increased.
So light can make it faster, and you can get more stuff out there, but it's not going to make it faster than light. That's still your limit.
Exactly.
You've got some hard stops in there. Yeah.
Yeah, it's the speed of light is the speed of light. That's all you can do. And then building on the moon, I would assume that we start with some remote controlled or self-controlled systems. And then you're probably going to try and use the regolith on the moon. So it's the sand to 3D print.
Which, have you seen those? They've done some great work on that.
I would probably try to dig. If I were to be there, I would try to dig.
Get me away from that radiation. Yeah. That's it. I'm with you.
I would probably try to dig. People claim that building on top is easier. I don't know.
Have you seen the inflatables, where they've got these inflatable... And then they cover it with that. They cover that with a regolith, which I thought was kind of interesting.
Also, that works. Yeah. Yes. Yeah. Also, that works. And
I don't think I'd want to be in a tent. I just don't know how comfy I'd feel in a tent on the moon.
I mean, the thing is, if I were to travel to the moon, I would want to be under a glass sphere, right? You would want to be able to look out, even if it's
that's true. What's the point of being there?
Thick.
Yeah, I could just dig a hole in my backyard and sit in there.
Yeah, I mean,
I'm on the moon.
It's dangerous.
Yeah,
right.
Yeah,
so it's you die basically. Whatever goes wrong, you die.
Yeah.
Yeah,
it's not I'm with the robots. Give me a pair of goggles and let me drive around on the moon. I'm fine with that. I don't want to, but I don't need to be there.
I would rather go there than download.
Really?
So I would be the guinea pig for going to the moon or to Mars.
What if you're downloaded and then sent to the moon? Then you could go and visit all of these places.
And then into a robot, and then
see?
We could talk about things. Probably not to Mars.
Okay.
I think I would, because that's too far away. That's just too far away. But the moon is kind of. I would love to go to the moon. I really would.
I would like to. The moon does seem kind of interesting, because that's like, I feel like you could do that in, that's a month or whatever it is.
That's not a month, and you can evacuate. And
Mars is for life. Mars is
and
a short life. Yeah.
If you don't die on your way there, you're going to die there. So, yes, the moon is, and maybe, 100 or 200 years down the line, things might be different, but from what I'm seeing right now, the moon.
Or an asteroid. I've always thought the asteroid thing would be fun. Go visit an asteroid. The fact that was it Bennu that came in and scooped up a chunk of, that's cool to me.
Yeah, that's a sure rendezvous with death. The moon. I vouch for sending my satellites to Mars.
Would you like to join me on a sure rendezvous with death? Yes.
I'm sure there are people. So
yeah. My wife says that when she goes, she wants to be eaten by a polar bear, and I can think of nothing more miserable than that myself. So
there you go. Yeah, there you go. But to answer that, yes, I guess remote in the beginning, and then 3D printing, and that's probably also autonomous and some digging and
it's
remote controlled.
It's almost like a combination of remote controlled and autonomous. It's almost like suggestible robots, where you just sort of basically you tell them what you want to do, and they go and figure out how to do it. Yeah, and I love that stuff. I mean. Like, I'm convinced that the first aliens we meet are going to be like Transformers, because they're going to be whatever robotic systems were sent out by some other planet somewhere, So, anyways. All right. So Gopher Fluffernutt. Hello, Gopher Fluffernutt. Says, what would likely be the most useful application of quantum computing to the average person?
So I guess the security that comes with encryption is the one that I would go
Smart.
to. Yeah. And it's perhaps not the individual one, but it's the security that comes for the individual from understanding our adversaries. Right. And that's a very wide kind of thing, and maybe an unpopular opinion, but I guess that is what it is. And then, as I said, potentially better improved climate and weather models.
That's pretty good. I mean, I'm on board with even just those two things would be.
And then for yes, you can do your own calculations, but I don't. So, again, narrow-minded. I don't know what would be my personal use of a quantum computer, because I don't need that high-performance computing in my private life.
Right.
Gaming, okay.
You've got your Legion. You've got your laptop.
My Legion,
yeah.
And there's gaming computers. I mean. Most of these things don't require any more than that. A stable internet connection and a good NVIDIA card, and that's that. And so, yeah.
I like the simulation side. I'd love to use it I'd love to see what it could simulate. That's sort of my fascination with that stuff.
Most of the simulations as a private person that you not a company, not a research institute, but that you as an individual would want to.
Yeah, I'm not doing that in my garage.
They are
partially because it's so freaking cold right now. That's why I'm up here. Yeah.
They're probably good to go for a normal high performance computer, or even for your gaming computer.
Yeah. Is it going to be? It's not going to be cheaper, is it? It's not going to be cheaper computing, because the GPUs are so freaking expensive right now. I've actually been looking at getting older GPUs that have a chunk of VRAM in them, and then maybe linking them together, because that would. While it's not as fast, it would still be able to do the AI stuff, which would be kind of fun to play with. But now, I'm babbling.
Yeah. So I guess it's not. There's the computer power just comes at a cost for quantum computing. So you get enhanced computing powers, but you pay for it. And I don't see how the individual, outside of what I said, like the general improvement, would benefit. Again, my small-mindedness to that.
There's no way someone could build a quantum computer in their garage. Is there could you, or not, maybe obviously not a super functioning one, but is there a way to sort of simulate or create something of a quantum type of?
I mean, it is not impossible.
It sounds like a silly question, I guess, once I've said it, but
No, you need to have a good understanding of what you're doing.
Yeah.
You need to have a good understanding as to how you entangle different qubits. You probably want to start with one qubit and take it from there. And then if any of your listeners would really like to try it, I suggest to take a look at an NV Center in Diamond. And then export control is probably a big friend of yours, and you'll have to there's
export control. What's export control?
Export control is you cannot export any goods that you have into foreign countries. And these things are very heavily regulated. And quantum technologies usually also are rather regulated because
I didn't even think of that.
You can do so many.
Of course.
Yeah. Export control is a big thing. And the big thing for the NV center in diamond is you need to somehow get the crystal with the NV center in it.
Right, right.
And since that can be thrown at so many problems, it's of course of high interest for many, many people, and so you can't get your hands on it freely. But so that would be the same story as trying to build your own fusion reactor or fission reactor in your garage, because you need to have these controlled substance in the middle.
There are parts they're not going to sell you.
Yeah, there are parts that are difficult to come by. As long as you say an American trying to do this in America, you're probably going to get it. And you will not get asked too many questions, but if you try to do that somewhere else in the world and try to get it from it, it's difficult. Anyway.
Yeah.
But with an NV center in diamond, a couple of lasers, some money to spare and some time to spare.
It's possible.
I don't think there is too big of an issue of building individual qubit computers.
Well, no one's giving it to me because I'm known for destroying parts of solar systems. So yeah, that's not.
I also just destroy stuff, but so it is not impossible. You need to be a little skilled,
right?
And I would suggest to try and build a magnetometer as opposed to a quantum computer.
Oh, okay.
But yes, it's.
So that we're just using lasers to detect
the Zeeman splitting in an NV center, for instance. Yes.
Neat. Okay.
I would definitely try that as opposed to trying to build a quantum computer.
You gonna put that on Instructables? Is that gonna be your next Instructable thing?
That's just me.
Yeah.
So.
No, I love that. That's actually perfect because that's the kind of. I mean, in a way, that makes more sense because it's a much more practical and visible use of it. You know.
Yeah. Yeah.
And of course, as like we've said, you can also go onto these websites and do the quantum computing in the cloud anyway. Someone else pays all the bills. It's great. Let me check for questions. We're almost there. Thank you so much, Lisa. I can't believe we're but I think this is the last question, in fact. And it says from Chris Martin says, question for the Quantum Queen. I'm so sorry. Have you considered integrating quantum mechanics and relativity via information theory? Example, E equals mc squared equals ki, where k is the mass entropy. Someone is flexing here. Is the mass entropy constant, and L is the. I'm sorry, I'm screwing this up, aren't I? And
no worries.
Does this make sense to you?
So the thing is, information theory for me is something that is not my field of expertise, and I won't be able to do that.
Right.
However, trying to integrate quantum mechanics with relativity is the big prize. It's the holy grail. It's the thing we all want, and whoever gets to do that wins the Nobel Prize or can conclusively show that it's not possible.
Right.
Either way, you are going to win a Nobel Prize. And I don't know if we talked about that last time. I would really like to do the experiment on that, trying to use large molecules and build a machine that can actually test the limits of quantum mechanics by looking into gravitational collapse of the wave function. So I would love to do that. This is the question in quantum mechanics that needs to be answered, or the question that I feel needs to be answered. I guess other people would rather like to know about quantum computing, but this, as a scientist, is a question that gets me super excited.
Yeah. Where's that edge? Where does it stop?
Where's that edge? Why does it stop? How can I then make use of where it stops and stuff like that?
And is there an edge? Is there a difference? Is there
an edge? Yeah. Or is our world just simply too hot and too complicated for it to work, for us to see the effects? Because if you drive with your car towards a bridge, you're probably going to crash as opposed to be 2 times in existence afterwards.
Yeah, I'm not going to take that gamble myself. Yeah, I don't like the odds, so to speak. Yeah.
No. That's not a good odds to have.
I'm too big and squishy.
Yeah, I know. It's bad. Me too. So even a mouse would be. So it might be on a planetary scale that we can see these things again and stuff like that. So this is all. But this is where, for me, quantum mechanics gets super exciting. And if you don't stop me now, I will talk for the next 4 hours about high mass interference and why quantum mechanics and relativity are so difficult to combine, and as to why I love that so much.
So we should, okay. So that should be a topic for another day. You're saying that's
yeah. I think what I'm trying to say is don't start me talking about it because
got it. It's funny because I was going to say I was going to say, what are you doing there? Yeah. Okay. All right. But that's,
I mean, we can, but
that is
I'm
a fascinating, it is a fascinating thing though, because you did talk about this before a little bit. And I invite everyone, if you like this, then you're going to love the one we did, the first one we did, where we didn't even know each other very well. And talking about where is that, we don't even know if this whole thing works at massive distances, right? I mean, we only know as far as we've been able to separate these entangled things and stuff, right? So there's a whole bunch of stuff. I mean, this has got to be a great field to get into now, isn't it?
It is. Now is the time to get into it. This year is the official UNESCO year of quantum physics.
Right. Oh, that's right. I was talking to the Quantum Village folks. Do you know the Quantum Village folks?
There are so many quantum villages now that I've lost count.
These are the DEF CON folks who have a quantum village. They are really fun bunch. Really fun.
There you go.
It makes me want to go to. I mean, I always want to go to DEF CON, but it just they were talking about some really fun stuff that they're working on, and actually I should put you in touch with them because they're talking about outreach. I mean, you've got a whole hacker culture thing on that as well, and they're really big on talking about how does this stuff work and how should it work and what questions should we be asking and stuff. So
absolutely. So, but yes, so there are. It is a fun time to get into it. It's I guess it's almost easy to get into it. You might, because people are looking for experts or for workforce in the field, as a lot of the field is, since there's such a high industrial interest. A lot of people get into industry, get sucked away from the universities into industry and research institutions into industry. There's a lot of startups right now, which means that at the universities and research institutes, there's a lot of open positions in the field of quantum technologies or quantum mechanics. So it's a great time to get into it.
What do you need to get into it? What's sort of required to get into it? I mean, I'm assuming some math.
Yeah, what really helps, is a major. I don't know about the American system, but say a bachelor or perhaps a master in physics or engineering, something of that. You can even do it with math. So some STEM, medicine, maybe not that much, but for the rest, that really helps.
Right.
It really, really helps. And then you don't need the doctorate. You can either gain that or just not have it.
Right.
And you also, so I myself do not have a doctorate in quantum physics.
But you are a doctor.
I am a doctor.
Yes.
I have a doctor in plasma physics.
Ah, very good.
So
why haven't we talked about that? Well, because today
we can also talk about plasma physics.
Yeah.
I'm happy to talk about plasma physics. I know a lot of stuff about plasma physics.
We didn't even have plasma when I was a kid. They hadn't really, the textbooks hadn't caught up to it being a state of matter when I was learning science. In the dinosaurs.
And condensates are also a state of matter, and they are, so usually even if people talk about...
Oh, they get their own state.
It's their own state.
Wow.
There is a phase transition and everything. It's its own state.
Wow.
So you get even one state more than...
So we could find even more states. There could be more states we don't even...
There could be more states.
Wow.
I mean, it's hard to think about more states, but there could be more states, yes.
Wow. Lisa, I should wrap this up because we've been going for over 2 hours now. You are, and I'm only stopping it because, frankly, I don't want you to drop of exhaustion because this is just amazing. I mean, I'll just zip through some of the tech stuff. The Quantum Village people, no, that's not what I meant, Alan Forbes. They are not the YMCA folks. This is the...
Well, it's the Q's. It's the Q folks.
Q, yes, exactly.
It's just Q.
It's, oh my God, Alan's even got lyrics for it. It's fun to stay at the up, down, charm, top.
You go.
You quantum nerds. So thank you to Alan for that. Hello, Spec Blue. I saw somewhere in there, Gimpy G. Welcome, Lance. Oh my God, there's so many people. Oh my God, this is people like quantum or people like Lisa. That's what it is. Alex, Daniel. Oh, I can't get through everybody. But thank you so much for being here. I'm amazed. I'm always amazed that people, want to listen in on these chats, and thank you so much for the questions. Thank you, Agne, again for handling the questions. And I don't know if Cal is in there, but if you're in there, thank you much for being there. Let's wrap it up. Let's get you to your wine and cheese. Lisa, thank you so much. Is there anything you would like to share with people before we go? Are there any links that they should be looking at? Is there, if we want to know more about Lisa and her quantum life, where do people find that out?
So you can find me on the DLR homepage, which is dlr.de. Rather straightforward. And since it's the quantum year, if you just plug that in, you see me on the front page, sitting there in the same picture that is used for your advertisement.
Which is a great picture, by the way. I'm so jealous. If I ever come and visit, I'm gonna ask for that little hairnet and the thing. Yeah.
I think that is actually a movie. It's made for a film. There's a film where this kind of picture is in moving sort of environment in it. I can send.
Oh, really? Oh, it's a still from the movie?
It's a still from a movie. So
not
from a play,
like a documentary.
From a no. It's more of a trailer type of thing. What we're doing at the
so I didn't know you had a trailer, Lisa. I would have.
We have sort of a trailer.
Very cool.
So DLRDE is, I guess, where you go. And then if you're still not satisfied, you could go to the Institute for Satellite Geodesy and Inertial Sensing. So you put the dlr.de/si, and then you'll find our institute
/SI capital or
just SI.
Sorry. Okay.
Just SI.
There you go. I've tossed it into the chat for people as well. So.
And then you will find the Institute for Satellite Geodesy and Inertial Sensing, and this is where I'm based.
And what are you up to now? What's next for you? What's the focus right now?
There is some. As always, there's always some reviews to go through. So There's a big review coming up this year. The next one is to prepare McKee for ESA, to get ESA, to convince ESA to launch us to Mars.
Ooh, who do we talk to? Is anyone we've spoken to we can bother for you? No.
I don't think so.
Okay, right.
I just have to do some lobby work with politicians all over Europe and make sure that they understand what's happening. And then I hope we will build the first systems for BCAL, to verify that our systems work and have that ready for launch to the ISS. Yes, I guess.
And then Mars. And then
Mars.
And then sensing Mars.
And then sensing Mars. And I would be, So there's a lot of things to be excited about. And it goes. Sometimes I get overwhelmed by the day-to-day, but it's nice to remind myself of these things.
Yeah, it's sort of important to have the big goals, but it's also I have a tendency to get lost in the sea of possibilities and forget that I've got to send Zoom links and things like that. So and
for me the day-to-day is sometimes so overwhelming that I forget what I'm doing it for. So sometimes it's nice to think about, oh look, this is why you're so excited about it.
Someone said, I can't remember, whether I've stolen it from someone but it's something that I sort of locked onto, was that we tend to put off what we love to the end of the day so it doesn't get done. We get all of the boring administrative life stuff, and then you get to like 6 or 7 p.m. and you're like, oh, I just got to have dinner and go to bed or whatever. It's just, and really what we should be doing is waking up and working on the thing that we want to do. You know what I mean? Like, it's such a weird mixed up world that we live in on that,
I love my job. And today I just did exactly that. I waited till the end of my day to get to talk to you.
I see what you did there. Wow, you're good.
Yeah, talk about my manipulation.
Forget sensors. You're going to own Mars. You're going to be the queen of Mars the next time we talk. Those politicians aren't going to know what's coming.
I don't know. But so I love my job. I love really, it's amazing. The day-to-day sometimes get a bit overwhelming, and of course there's some emails that I didn't respond to and stuff that just piles up. But I love the people I work with. It's every day. It's exciting. It's super interesting to talk about the challenges, the opportunities, ways to go, industrial partners, academic partners, politicians, whatever. There's a whole world out there, and I want to make it a better place.
Well, I got to say, you are amazing at sharing that and that excitement, because I get excited talking to you about it. I can see in the chat how excited everyone else is as well. So thank you. Thank you for skipping some emails and spending so much quality time with us. That was, as always, just fantastic. I think I'm just going to stop calling it I'm with Genius. Just call it I'm with Lisa, because it's so much fun. Thank you. Thank you very much.
Thank you so much.
And thank you, chat. Thank you, Agne, again. We'll be back next week with some more exciting science. Although it's going to be hard to beat this, Lisa. We'll have to get you as a regular guest on the. So I will say to everyone, until we geek again, I will say, be brave, be kind, be brilliant, and thank you all for joining us on this. My